Chapter 27 of A History of Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in December 2020. A History of Astronomy by Walter W. Bryant. Chapter 27. Comets, Meteors, Zodiacal Light. The remaining members of the solar system must not be overlooked. Comets, which even now to the disordered imagination, or rather perhaps to the business instinct of a Zadkiel, are regarded as portents, lost their terrifying character to a considerable extent when the recognition of their periodicity in some cases brought the inference that their motions were subject to the same laws as those of the planets, the chief outstanding difference being the eccentricity, which, though in occasional instances not much greater than those of one or two exceptional asteroids, approaches, reaches, and possibly exceeds unity, thus providing highly elongated ellipses, parabolas, and it may be hyperbolas for the apparent orbits. In the first of these cases the comet is periodic, but most observed comets belong to the second class, or rather cannot be distinguished from it owing to the extreme length and uncertainty of the periods. The third case, of which there are few absolutely certain instances strictly speaking, is that of what may be called temporary members of the system, though a really parabolic orbit may also be regarded as that of a temporary member also. The first great comet of the period we are now considering was the celebrated 1858 comet of Donati, the finest comet within living memory, though not considered quite so bright as that of 1811. Visible to the naked eye for 16 weeks, and to the telescopes of the time for 9 months, this comet was exhaustively observed. Its brightness, which at maximum surpassed that of Arcturus, was a notable instance of the great increase in actual brightness near the Sun, which far exceeded that predicted by theory from its relative distances from the Earth and the Sun. Its tail, or rather tails, were well placed for observation, and as one after another became visible, the main portion curved with 2 straight tangents. The idea suggested by Olbers that these tails were different kinds of matter unequally repelled by the Sun seemed almost to require no further proof. The head of the comet was also in violent agitation, throwing off veils of gauzy matter towards the Sun to curve back like fountains after a comparatively short time, the general appearance being that of a hollow cone or cones seen brightest at 2 opposite edges. This comet was too early for the spectroscope. Its brightness was analyzed only by the polariscope, an instrument often disappointing in its results. In this case, the analysis showed no evidence that the brightness, although only about 3% of it could be accounted for by its position, was at all intrinsic, such as might be caused by a great increase of temperature in careering with increasing velocity through a medium even of great tenuity, or possibly by the friction of its agitated parts, or, as was commonly suggested, by ignition in the heat of the Sun's rays. Simple reflected light was the unsatisfactory verdict of the polariscope, and there was then no higher court of appeal. So all that issued from the mass of observations was a very accurate determination of the orbit, giving a period of 2,000 years. In 1861 the Earth passed for some hours through the tail of a comet, to the depth, computed by Liais from the observations of the discoverer John Tebbutt of New South Wales, and his own at Rio de Janeiro, of 300,000 miles. There was no other evidence, except the observed motion of the comet, that the Earth had actually passed through the tail, which caused no apparent effect, electrical or otherwise, distinctly traceable to the unusual environment. Within the next few years, two celebrated comets were discovered, first designated simply comets 1862-3 and 1866-1, but since the labors of successive investigators were brought to a final conclusion by Schiaparelli, known as the comets of the Perseids and Leonids respectively. The first of these reached practically the second magnitude, while the other was very faint and showed no tail. The connection between comets and meteors, definitely pointed out by Schiaparelli, had been in a hazy sort of way present to the minds of investigators for some time before, though the original idea of meteors was that they were akin to fire, damp, small clouds of marsh gas suddenly ignited in the air. Chladni, in 1794, stated in concrete form a notion vaguely entertained by Halley that they were cosmic atoms, made white-hot by friction in the atmosphere. Velocities were determined from simultaneous observations sufficiently far apart to indicate the height of the meteor, and these velocities turned out to be great enough for bodies moving like planets. Laplace and others, however, maintained that they were ejected from lunar volcanoes. But the uncertainty was to a great extent dispelled by the marvelous shower of meteors on the night of November 12, 1833. The display was at its best in America, and at Boston it was calculated, actual counting being impossible, that 240,000 were visible during the 9 hours from the time the shower commenced until daybreak put an end to the sight. The illuminating feature of this splendid apparition was the circumstance that all the meteors seemed to come from the same part of the sky, the sickle in the constellation of Leo, all paths accurately drawn diverging from a single point, which had no relation to the earth, but moved with the stars. It was speedily deduced that the meteors were describing orbits round the sun, and since a display on a small scale had been seen just a year previously in the Old World, these orbits must meet that of the earth at the point reached by it on November 12th. Meteors were at once recognized as providing a new field of astronomy. Humboldt had witnessed a shower almost as brilliant on the same night of the year 1799, and had also noted that the bright paths were directed from a single radiant, but no theory had been placed upon his observation, and the first guess at the Leonid period, by Professor Olmsted of Yale, was a half-yearly one, on the assumption that the aphelion was reached on November 12 every year. But the display in 1834 was not a great one, and each year saw still less, and the next conjecture, by Olbers in 1837, was founded on Humboldt's observation, and suggested a period of 34 years, fixing the next great display in November 1867. The August meteors, or Perseids, were also the subject of inquiry, and the fact that they also appeared annually discredited Olmsted's idea that the Leonids were a cloud of particles with a short period, suggesting instead a ring of particles extending round an orbit nearly, if not quite, intersecting that of the Earth at the point reached by it on November 12. Nothing more was done in the way of advance for a long time, in fact, until Professor H. A. Newton took up the investigation at Yale in 1864. Consulting old records, he identified the Leonids with a historic display on October 13, 902, when Taormina was captured by the Saracens, and deduced a period of 33¼ years from successive appearances, which recurred with a retardation of 1 day in 70 years. He predicted a fine display for the night of November 13, 1866. 4 other periods were found, which would account for the interval of 33 or 34 years, but the loss of 1 day in 70 years provided Professor Adams with a method of mathematical investigation, since it was due to the advance of the node of the orbit caused by planetary perturbations. His result, which dismissed as impossible all but the 33¼ year period, was not reached until a few months after Professor Newton's prophecy was fulfilled. Preparations had been made in advance. At Greenwich, for instance, the new branch of routine observation was introduced in 1865, and a fair number of Leonids observed. But the great display came on the predicted night in 1866, bringing crowds of meteors, many very bright, and some as bright as Venus. The greatest rate estimated for an hour averaged more than 1 per second, the actual numbers recorded at Greenwich being 4,858 between 1 and 2 o'clock on the morning of the 14th. Schiaparelli's investigation, stimulated by this magnificent display, showed that meteors travel much faster than the Earth, so that their orbits are much larger than that of the Earth, and their motion like those of comets rather than of planets. He next inferred that, in general, comets and meteors come from outside the solar system, are temporarily drawn into it by the sun, and occasionally kept within it by the retarding action of a planet. Lastly, he identified the orbit of the Perseids with that of the bright comet of 1862. Soon afterwards, Dr. Peters of Altona, from Le Verrier's new elements of the Leonid swarm, identified the orbit with that of the comet of 1866, Schiaparelli immediately afterwards independently confirming the result. Professor Weiss similarly connected the April Lyrids with a comet seen in 1861, and the Andromedes of late November with Biela's comet. Professor Alexander Herschel took up the subject with enthusiasm, and by 1878 compiled a list of no fewer than 76 comets, known or suspected to be connected with meteor swarms. The underlying principle of this idea of identity or close similarity between comets and meteors had made its appearance more than once before, and in 1861 Professor Kirkwood had argued, from the known appearance of Biela's comet in 2 portions, that the Sun had an effect on comet nuclei whose tendency was to split them up, and suggested that the periodic meteors might be the debris of old shattered comets, whose cohesion being destroyed leaves them nothing but a range of small particles distributed along or near the old orbit. From the fact that the main swarm of the Leonids seemed to take about 3 years in passing the point of approach to the Earth's orbit, while the Perseids seemed more evenly distributed, Le Verrier argued that these are successive stages of disintegration, the swarm lengthening out until it reaches the stage of a closed ring of particles. He inferred not only that the Perseids were an older formation, but assigned a date for the first appearance of the Leonids in the solar system in AD 126, when Uranus, by his calculations, must have been close to the parent comet of the whole system, the comet of 1866 being only regarded as a fragment. But Biela's comet, which appeared in 2 portions in 1892, had not been seen since, though carefully sought, and it was naturally suggested that perhaps this might be regarded as a crucial test. Previous showers from the point near Gamma Andromedae, where the orbit of Biela's comet appeared to meet the Earth's track, had been noticed on December 6, 1798, and again in 1830, 1838, and 1847. So Weiss, as we have seen, and independently d'Arrest and Gallet, inferred that the orbits were identical, and that the date would be getting earlier in the year, since, owing to the motion of the comet being retrograde, the motion of the node would be in the opposite direction to that of the Leonids. The Andromedes were duly observed on November 30, 1867. The comet was due in 1872, and Gallet suggested November 28 as the probable date of the swarm of meteors into which the comet might have broken up. It actually arrived on November 27, when the display was nearly as striking as that of the Leonids 6 years before, the Andromedes or Bielids being slower in apparent motion, as they were traveling to overtake the Earth instead of meeting it. At times they were said to average 4 or 5 per second, and some were fireballs apparently as large as the Moon. A search suggested by Professor Klinkerfues to see if the comet itself had gone by during the swarm resulted in the discovery of a faint comet, which, though not Biela's, probably belonged to the system. The period of the comet being about 6½ years, a return of the swarm was expected in November 1885, and expectation was more than fulfilled, for the swarm, where not masked by cloud, showed more numerous and larger meteors than that of 1872. Professor Newton estimated 75,000 per hour in the densest part of the swarm, and a density of 1 to a cubical space of 20 miles edge. A near approach to Jupiter in 1841 was the probable deciding factor in the disintegration of this system. In 1892, a fine shower of Andromedes was seen in America, though far less striking than that of 1885. Its appearance so early as November 23 suggested that this was not the main swarm, but an associated branch. The next expected displays have failed to appear in any numbers, the first in 1899 and the next in 1905. So, perhaps, planetary perturbations have so modified the orbit that it no longer passes near enough to the Earth to display more than a few stragglers. The Leonid display expected in 1899 also failed, as had been predicted by Dr. Johnstone Stoney of Dublin and Dr. Downing of the Nautical Almanac Office, would be the result of perturbations by Jupiter and Saturn. Search at the usual dates will be maintained, as meteors are more frequent at those special epochs, but there is now no definite expectation of any such vivid displays as the various November showers of 1833, 1866, 1872, and 1885. Progress has been made in the direction of accuracy in the determination of paths by the use of a meteorograph, a camera directed near the expected radiant so that any meteor bright enough to impress its trail on the plate could be accurately referred to the stellar images surrounding it, comparison with a similar photograph of the same region from a different station yielding exact data for the determination of the real path, height, and velocity of the meteor. From the connection, now regarded as proved, between comets and meteors, emerges the certainty that comets are temporary bodies, that they break up into smaller comets or streams of meteors, and ultimately to some extent are absorbed by more permanent members of the solar system. The question whether aerolites, meteoritic stones that actually fall on the Earth without being pulverized, are of the same class is not so well determined. Cermak and others postulate a different origin. Some, following Laplace, assume a lunar volcanic source. Others conjecture a source in one or other of the great planets. Others again, like Sir Robert Ball, attribute them to terrestrial volcanoes of a bygone day, whose missiles, hurled out when the explosive force was far greater than it is now, have been constrained to revolve about the Sun in orbits bound at intervals to pass through the point of origin, and so, in course of time, to fall to Earth again. It has even been supposed that they may come from the Sun. But no real distinction can be drawn between the meteors that are seen to burn up and those that burst into sizable fragments, or reach the Earth without attaining an explosive temperature. Detonating fireballs have been seen apparently belonging to a known radiant, and aerolites have occasionally fallen during meteoric displays, the coincidence being very likely fortuitous. Professor Newton considered that the larger meteorites, whose paths were traced by him, appeared to have their perihelia in the outer portion of the space between the Earth and the Sun to correspond more closely with short-period comets, and to be more planetary in character than the recognized comet-meteor swarms. The pursuit of meteoric astronomy in this country has brought to the fore an amateur observer, W. F. Denning of Bristol, to whom reference has already been made in connection with planetary observations. By unremitting diligence in watching for known showers, and in collating the results of other observers, he has computed radiant points by the hundred, and reached a leading place among the world's astronomical specialists, at a sacrifice of his own time and means, which has lately found recognition in the form of a civil list pension. One of his most striking achievements has been the proof of the existence, long denied as impossible, of a distinct class of meteors whose radiance remained fixed for months instead of showing the daily motion of the Earth by a gradual shift in the sky. The first hypothesis was that this could only be explained by the assumption that the Earth's velocity was negligible in comparison with that of the meteors, but, as Ranyard calculated, this implies a velocity for them of at least 880 miles a second, which is out of the question. Hence, for a long time Denning's discovery was scouted, but the accumulation of evidence still went on, and the fact obtained grudging recognition, while the suggested explanation had to give way, the motion of the meteors, much slower when overtaking the Earth than when meeting it, proving that no such enormous velocities were necessary. The contention of Brédikhine that the community of radiant is only apparent, and that the successive meteors belong to several different swarms, seems to postulate such a vast number of coincidences as to create an equally refractory difficulty. Professor Turner's explanation is at least plausible, insofar as it gets rid of the fortuitous nature of the coincidences. He attributes the successive swarms from the same apparent, but really slightly different radiant, to be due to the cumulative effect of the Earth's attraction, exercised at regular intervals on neighboring members of the swarm. The details of the explanation are not sufficiently convincing to be regarded as settling the question, which still awaits solution. The Perseid radiant has been questioned for the opposite reason, the motion in a period of nearly 6 weeks, for which separate radiants have been computed, being palpably greater than that of the Earth in its orbit. But Dr. Kleiber, making due allowance for the Earth's motion and for its attraction, proved that all the radiants belong to a compact group, of which the comet radiant is the center. Even so, however, the Perseid stream is of enormous width. We must now resume the consideration of comets. The application of the spectroscope was not much too late for Donati's great comet. He himself was the first to obtain a practical result with the new weapon of research, for applying it to a comet which appeared in 1864 and reached the second magnitude, he found the spectrum to consist of 3 bright bands, yellow, green, and blue, with dark intervals between. This promptly negatived the conclusion suggested by the polariscope observations and proved the existence of luminous gas. In 1868, observing Winneke's comet, Huggins identified the bands as belonging to a hydrocarbon spectrum, a similar one being produced by electric discharge through a vacuum tube containing olefiant gas. Vogel and Hasselberg increased the resemblance in later experiments by adding a little carbonic oxide. 18 comets from 1868 to 1880 showed the same typical spectrum, but it was impossible to imitate it by any other method but electric discharge, as a continuous current showed only the spectrum of the carbonic oxide. But 2 comets before that period, and some since, failed to show the hydrocarbon spectrum. Those observed by Huggins in 1866 and 1867 showed a continuous spectrum crossed by one green ray, generally associated with nebulae. Comet Holmes, 1892, gave a weak continuous spectrum, but the Great Southern Comet of 1901, which also showed an almost continuous spectrum, stifled the theory that the absence of self-luminosity pointed to a state of decay. In 1874, a much brighter comet, discovered at Marseille by Kodja, not only enabled Vogel and Huggins, with the addition of Brédikhine, to recognize the typical hydrocarbon spectrum, but also gave Father Secchi at Rome the opportunity of detecting 2 more bands in the red and violet. It is probable that these should be visible in the other comets also, but for the absorption of the fainter bands by the atmosphere. Zöllner's investigations have caused it to be accepted as a fact that the incandescence of the comet gases is not due to heat but to electricity, the effect of the solar radiation and other changes due to the rapid motion of the nucleus being manifested in this way rather than by a simple increase of temperature. It was Zöllner also who first definitely formulated the physical theory of repulsion to account for the appearance of comets' tails, though, as we have seen, Olbers had suggested the idea of repulsion. Bessel applied it in the discussion of Halley's comet, and Norton in that of Donati. Since gravitational pull depends on the mass of a particle and electrical repulsion on its sectional area, it follows that, in dealing with very small particles below a certain limiting size, the repulsion increases relatively to the attraction as the size of the particles diminishes, so that, beyond another limit, different for particles of different substances, the repulsion actually overbalances the attraction. Zöllner pointed out that while the more massive nucleus of a comet obeys the laws of gravitation, the very finely divided particles shed from it in an electrified condition follow perforce the lines of electrical repulsion and stretch away from the sun in the form of tails. Brédikhine, whose enthusiasm was kindled by his observation of Kodja's comet in 1874, devoted himself to the subject of this repulsive force, which he computed to be different from what he had computed for other comets a dozen years previously, and a few years later, having completed his investigations of 36 well-observed comets, he confirmed an idea, at which he hinted in 1877, by announcing that all comets' tails are divided into 3 classes, according as the repulsive force is much greater than, nearly equal to, or distinctly less than the solar gravitation. The actual figures given were, for the first class, 14 times solar gravity, giving rise to very long, straight tails. For the second, the scimitar tails, a force varying from a half to more than twice the solar gravity from one edge to the other, and having at the axis a value only 10% in excess of the opposed attraction, and for the third, the short brush tails, from 10 to 30% of the sun's gravity. The third class does not appear to occur alone in bright comets. In fact, it seems that in general more than one type is present. Brédikhine was, however, not satisfied, as his predecessors had been, to assume that the classes indicated different kinds of matter, but proceeded to identify them from the relations of the requisite forces which he assumed to be inversely proportional to the atomic weights. The 3 substances he announced were hydrogen, hydrocarbons, and iron. Of these, iron appears often in meteorites, and its presence in comets is quite possible, and the very width of the brush-like tails of the third class shows that iron could not be the only substance represented, a suggestion that would have been far from plausible. Hydrocarbons had been proved to exist in comets, and so only the hydrogen remained doubtful, as it has never been detected in comets by its characteristic spectral emission lines. The modern ideas of light pressure or radiation pressure, enunciated originally by Fitzgerald and afterwards by Arrhenius and others, tend to render Bredikhin's chemical theory unnecessary, the various modes of action of the electricity itself being quite sufficient to account for the undoubted type variations. But this theory is far from being crystallized into dogma, and is still in the hands of critics and experimenters. 5 notable comets appeared soon after the publication of Bredikhin's hypothesis. The first of them was the Great Southern Comet of 1880, conspicuous to the naked eye for 8 days, whose orbit so closely resembled that of the famous comet of 1843 that several theories were started to reconcile the apparent impossibility of identifying them as the same object. One very interesting suggestion of Klinkerfues was that the comet appeared in BC 371, next in AD 1668, and then in 1843 and 1880, a progressive decrease in velocity at each perihelion passage accounting for the shortening of the period. It happened that neither the comet of 1843 nor that of 1880 were observed over a sufficient arc to fix their period with any certainty. An appeal to Bredikhin's hypothesis showed that the great tail of the 1843 comet belonged to the hydrogen class, while no such tail, but only hydrocarbon tails, appeared in the new comet. Halley's comet having preserved its type was urged as an objection to the suggestion of type modification. The next comet, visible from May 1881 to February 1882, provided another problem, for its elements agreed with those of Bessel's comet of 1807. But the long period of observation asserted a period of not 74 years, but nearly 2,500 years, so it was in this case concluded that the 2 comets were portions of a parent comet, one of which lagged 74 years behind the other in the same orbit. The introduction of dry plates for photography took place in time for them to be employed in taking pictures of this comet, which were the first really successful comet photographs, though partial success had been reached so long previously as the time of Donati's comet. Of Tebbutt's comet, Janssen secured a very fine photograph, showing the head and 2½ degrees of tail, and Dr. Henry Draper another, showing 4 times the extension. The latter also photographed the spectrum, as also did Huggins, the result being to confirm the hydrocarbon identification by additional lines beyond the visible spectrum, and also to confirm the polariscope in regard to the presence of Fraunhofer lines denoting reflected sunlight. Comet Schaeberle, though not so bright as that of Tebbutt, was easily visible with it in the northern sky, a very unusual phenomenon. In the following year, 1882, Comet Wells made its appearance, and though not very conspicuous, as it kept near the Sun in direction, showed one feature quite new in comet spectra. On approaching the Sun, the carbon bands died out, being replaced by the bright D line of sodium, observed first at Dunecht and confirmed by Vogel at Potsdam. Hasselberg argued from this change of spectrum that the luminosity of the vapors must be electrical, as, if the only effect of the Sun were to raise the temperature, the sodium line might certainly become visible on that account, but the hydrocarbon lines would also persist. Other peculiarities were revealed by a successful spectrum photograph secured by Huggins. The last of the 5 comets was discovered independently by several observers in September 1882, and watched right up to the limb of the Sun at the Cape Observatory. After passing the Sun, it was easily visible in broad daylight, though still quite near the Sun, and was thus visible for 3 successive days. Its path also was so similar to those of the comets of 1843 and 1880 that it seemed to afford another step in Klinkerfues' suggested history, and the theory of retarded motion by a resisting medium near the Sun was freely urged again. But in this case the velocities before and after the perihelion passage were carefully compared, and found to show no trace of such a diminution. It was observed, moreover, to a greater distance from the Sun than any previous comet, nearly 500 million miles, the whole arc of observation covering 340 degrees. Kreutz ultimately deduced a period of about 800 years, not agreeing well with those of the other 2 comets of possibly common origin. But the difference in the length of the orbit is not an objection to the idea of a single parent body, since each fragment would necessarily suffer variations of constants peculiar to itself, and in elongated orbits of this kind the most likely alteration would be the extent of elongation or major axis. Rejecting as probably erroneous the earliest member assumed by Klinkerfues, whose inclusion is a distinct violation of the historic account of Aristotle, this made 4 members of the same family, and a 5th was discovered at Cordoba in 1887. One other comet is generally assigned to the same group, the one seen and photographed close to the Sun during the Egyptian eclipse of 1882. But the theory of disruption in this particular group received strong confirmation in the great comet of 1882, for early in October the nucleus began to divide first into 2 condensations, then into 3, and then 4. 3 months later 5 nuclei were seen in a row like pearls on a string by the late Dr. Common at Ealing. Moreover, Professor Barnard in October had seen 6 or 8 distinct cometary masses quite near the comet's head. The spectrum of the comet behaved like that of Comet Wells, but showed in addition to the sodium line 6 bright iron lines in the yellow and green, thus actually confirming an assumption underlying Bredikhin's hypothesis in regard to his 3rd type. The Dunecht observers, Copeland and Lohse, who made this discovery, also computed the velocity from the displacement of the lines. From the sodium line alone, Tollon of Nice confirmed this spectroscopic determination of velocity, which agreed very well with that computed from the actual positions of the comet, a strong testimony in favor of the spectroscope for line-of-sight investigations. As the comet receded from the Sun, the sodium lines gave place to those of hydrocarbon, as might have been expected. Another interesting comet, 1889-5, discovered by a very successful searcher, W.R. Brooks of Geneva, New York, was seen by Barnard at Lick Observatory to have thrown off 4 fragments, 2 very ephemeral, 1 remaining visible for a month, and the last more than 3 months, all however fading from sight before the parent comet, which has since returned alone in 1896 and 1903. The year 1892 saw 7 comets visible together. Of these the brightest was only of the 3rd magnitude, discovered by E. Swift, the photographs of which by Barnard and W. H. Pickering showed a great advance in that branch of astronomy. The accompanying plate is a recent example of Barnard's careful work. Another of the 7 was the first comet actually discovered by photography, being found by Professor Barnard to have impressed a faint trail on a photograph of stars in Aquila. Another interesting comet of the year was discovered by a London amateur, Edwin Holmes, and was remarkable for 2 features. One, a series of peculiar physical variations, including an unexpected brightening for 2 days, when it had already faded considerably, having been discovered after perihelion passage. The other, an eccentricity almost low enough for a minor planet, its orbit being also entirely between those of Mars and Jupiter. One conclusion of W. H. Pickering from observation of the comet 1892-1, E. Swift, was a solar repulsive force nearly 40 times that of gravitation, or 3 times as great as that required by Bredikhin's first type, and about double of the limit assigned from theory by Schwarzschild as the maximum possible effect of light pressure. Hussey also found a repulsion nearly as great in the case of another comet, 1893-2. But the light pressure theory is not the only one, as we have seen. Fessenden in 1896 supposed a negative charge on the Sun and on the particles of the tail, and a positive one on the nucleus. J. Thomson in 1902 suggested that if the Sun's rays induced the comet to give off negative ions, these would form a luminous tail. It is not clear how the Sun's rays would act, but it is possible that the ultraviolet rays might cause the emission of negative ions, which would be repelled by Hertzian waves, if any such were sent out by the Sun. Another theory depends on radioactivity in the nucleus itself, different forms of emanation giving rise to different tails. Among these theories, it can hardly be said that one really holds the field. Radioactivity in some form seems the most promising, perhaps because it is so revolutionary in regard to previous physical notions. Meanwhile, an American prize fund awards medals and prizes for cometary discoveries, and within the last 5 or 6 years, A. F. Lindemann of Sidmouth has, by offering premiums for such work, induced various computers to work out the definitive orbits of neglected comets, one of which, 1886-1, is claimed by Svestrup to be hyperbolic, and to suggest radiation pressure as affecting the observations. C. J. Murfield of Sydney, an assiduous worker in the same field, had already announced at least 2 hyperbolic comets, but not so well observed as 1886-1, which was visible for several months. The brightest comet of the last 20 years was the southern comet of 1901, not seen further north than the Lick Observatory, but very bright in the southern hemisphere. The next interesting return expected is of Halley's comet, which, according to a recent analysis by Messrs. Cowell and Crommelin of Greenwich Observatory, is due to reach perihelion again by the middle of May 1910, a date agreeing closely with that predicted by Pontécoulon. Before leaving this chapter, we may note that the year 1902 saw not only the largest meteorite for many years in the British Isles, the Crumlin meteorite, over 9 pounds in weight, but also the largest meteorite known to be in existence, the Mexican meteorite, measuring roughly 13 by 6 by 5 feet, and weighing about 50 tons, consisting mostly of iron, with a fair proportion of nickel, a very little cobalt and phosphorus, and traces of sulfur and silicon. We must also mention very briefly before leaving the consideration of the solar system 2 other almost certainly related phenomena, the zodiacal light and the Gegenschein or zodiacal counterglow. The first is a faint luminosity frequently noticed after sunset or before sunrise under favorable conditions near the equinoxes, especially in low latitudes, often visible all night in the tropics, extending along the direction of the zodiac or ecliptic, broader at the horizon but narrowing towards its visible extremity. It is supposed to indicate the presence of a vast concourse of atoms or corpuscles forming an enormous lens-shaped envelope to the Sun, either as distant extension of the outer corona or possibly impalpable remains of comets and meteors gradually drawing nearer to a final absorption as fuel into the solar fires. One of the numerous theories now discarded as to the source of the maintenance of solar heat was on these lines suggested by J.R. Meyer. But whatever the nature of the zodiacal light, the bodies, if such they be, offer no measurable resistance to the passage even of a comet, and an atmospheric explanation would seem more plausible could one be found to account for the invariable plane of the phenomenon, which is the main argument for its being a solar, or at any rate non-terrestrial, appendage. The Gegenschein also belongs to the ecliptic, and is a very faint luminous patch, about 12 degrees by 9 in extent, sometimes seen in the direction exactly opposite to the Sun. It is generally taken to represent some effect of the Earth's cone of shadow, or of the sunlight just beyond the shadow, but the details are uncertain. It has been considered probable, if not certain, of late years, that the zodiacal light and the Gegenschein are not distinct phenomena, inasmuch as they have at times been seen at favorable stations such as Arequipa, connected by faint zodiacal bands, leading to the inference of an extension of the formation, whatever it may be, far beyond the Earth's orbit. It has been argued in support of the zodiacal light being distinctly a solar appendage that it is only approximately an ecliptic phenomenon. Newcomb, in 1905, observed it due north at midnight from an alpine summit, and previous observations had connected it rather with the Sun's equatorial plane than with the ecliptic. It has, however, been photographed at Heidelberg and at Flagstaff, and the question of its axial plane ought to be settled in that way before long. If it is clearly zodiacal, it may probably represent byproducts, waste material left behind in the evolution of the system from the original nebula. If it can be referred to the Sun's equator, it is not impossible that the solar repulsive force can act at a distance greater than 100 million miles. In any case, the light is pronounced on spectroscopic evidence to be reflected sunlight, witnessing the presence of particles of some sort, and we must await the result of further investigations to determine its actual position, distance, and extent. End of chapter 27.
Chapter 28 of A History of Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marvin Benarescu. A History of Astronomy by Walter W. Bryant. Chapter 28. The Stars. Catalogues, Proper Motion, Parallax, Magnitude. Turning from the vast solar system to the incomparably greater stellar universe, of which it forms but a single speck, though from our point of view a by no means insignificant speck, we must first regard the stars as a whole, supplying as they do the relatively unchanging background against which the motions of the members of the solar system are thrown into prominence. The importance of accurate standard places of stars was long ago recognized, but comparatively few observatories, at any rate before the middle of the 19th century, devoted any considerable part of their energies to the production of catalogues. We have seen how Bessel's appreciation of the monumental labours of Bradley at Greenwich rendered his results available in the Fundamenta Astronomiae, and how Lecaille's work in the southern hemisphere provided a supplementary catalogue at the same epoch of the part of the sky not visible at Greenwich. The great work of Bradley has been re-reduced by Dr. Auwers of Berlin, with improved constants and tables, and still remains a standard catalogue after the lapse of a century and a half since the epoch of the observations. Another catalogue of nearly the same epoch was that of Tobias Meyer of Göttingen, which has also been re-reduced. With various epochs about the beginning of the last century, we find three other well-known catalogues: the Piazzi catalogue from Palermo observations by the discoverer of Ceres, that of Lalande from observations given in the Histoire Céleste taken at Paris by various observers and students, and a catalogue of circumpolar stars observed by Stephen Groombridge at Blackheath. The re-reduction of Piazzi's catalogue was recently undertaken, and also the re-observation of all the stars in it at observatories in Italy and America. Lalande's zone catalogue purports to contain nearly 50,000 stars, but as each observation was separately reduced, the real number of stars is not so great, since many of the bright stars have at least 5 entries, and Vega as many as 13. The British Association published the Lalande catalogue with epoch 1800, omitting certain zones near the North Pole, which were separately reduced by Fedorenko to the epoch 1790. The moving spirit of the British edition was Francis Baily, who devoted many years to the labour of making other people's observations available, beginning with those of Flamsteed, a century before Lalande. The Paris Observatory undertook the re-observation of Lalande stars, and the results of observations from 1837 to 1881, though only definitely devoted to that purpose in 1855, have now been published in 8 volumes, appearing at intervals from 1887 to 1902. Groombridge's stars, his own epoch being 1810, were re-observed at the Radcliffe Observatory, Oxford, with epoch 1845, and again towards the end of the century in Greenwich catalogues, in connection with which the re-reduction of Groombridge's original observations has recently been completed and published in 1905 by the Royal Observatory. Bessel's contribution was not confined to the reduction of Bradley's observations. His own zone observations at Königsberg fill 2 catalogues, epoch 1825, one dealing with stars within 15 degrees north or south of the equator, and the other with the 30 degrees of declination immediately north of the first catalogue, i.e. with declinations 15 to 45 degrees north of the equator. Argelander of Oobu, afterwards of Bonn, continued the zone observations from Bessel's northern limit to 10 degrees from the North Pole, epoch 1842, and from his southern limit to about 30 degrees south of the equator. The series of catalogues regularly published at Greenwich was commenced about this time, each embracing the stellar observations at the Royal Observatory for a period of from 6 to 10 years, the 12-year catalogue being simply a combination of 2 successive 6-year periods, a system introduced by Airy soon after his appointment. Many other catalogues belong also to the first part of the century, including those of Rümker at Hamburg, Santini at Padua, Taylor at Madras, recently re-reduced under the direction of A.M.W. Downing, Superintendent of the Nautical Almanac, Brisbane at Parramatta, Johnson at St. Helena, and others. (1850) was the epoch to which Lamonde's Munich zone observations were reduced, and also that of the British Association catalogue, produced by the indefatigable Baily, including all stars, to about the 6th magnitude, of which reliable observations had been published, and thus forming an invaluable work of reference. R.C. Carrington of Redhill applied himself to the observation of the polar cap north of Argelander's zone, and by his catalogue of stars from the pole to 81 degrees north declination, epoch 1855, in addition to his valuable sunspot observations, earned scientific recognition not often accorded to the later years of a man retiring from a commercial career. But 1855 is most celebrated as the epoch of the Bonn-Durchmusterung, carried out under Argelander and his successor Schönfeld. It comprises in several volumes a complete survey, down to a magnitude about 9.5, of the sky from the North Pole to 2 degrees south of the equator, and to an even fainter limit for the next 20 degrees south, included in Schönfeld's continuation. The places, though not of great refinement, are very approximate, and letters are suffixed to stars identified as having been found in certain standard catalogues. This great survey, once known as AZ, Argelanders zones, but properly referred to as BD, though still often quoted as DM, despite the fact that it is no longer the only Durchmusterung, was supplemented by Schönfeld with a series of large sectional maps showing, with meridians of right ascension and parallels of declination, every star in the BD. No previous star atlas could compare with these Bonn maps for such purposes as the identification of a field in which a comet had been observed, often far from the region covered by the ecliptic charts of Chacornac, Bremiker, and others. They contain about 324,000 stars, exclusive of Schönfeld's continuation, or 450,000 in all. In 1865, the Astronomische Gesellschaft, or German Astronomical Society, suggested obtaining fundamental observations of all but the faintest stars in Argelander zones, dividing the sky into suitable portions, zones of declination, corresponding to the position and equipment of 13 cooperating observatories. The epoch of the various resulting catalogues was fixed for 1875, but the work took a very long time to complete, and the results for the different zones are not of quite the same accuracy. The observatories, such as Helsingfors, Christiania, Leiden, Lund, Dorpat, and Washington, having, for obvious reasons, different atmospheric conditions, besides different instruments and observers. The next step was in the direction of standardizing the survey, but leading up to it was the work in the Southern Hemisphere. The chief catalogues produced there at the time having been B.A. Gould's Argentine General Catalogue from Cordoba observations, published in 1886, and Stone's Cape Catalogue for the epoch 1880. Stone's successor, Sir David Gill, who only recently retired from his post at the Cape, was struck with the clearness of the images of stars on photographs of the Great Comet of 1882, and, being anxious to extend Schönfeld's zones to the South Pole, determined to employ photography for the purpose. The result was the Cape photographic Durchmusterung, the photographic plates being taken in 4 years and reduced to the form of a catalogue in about 14 years by the labours principally of J.C. Kapteyn of Groningen. But not long after the commencement of the Cape survey, Gill suggested the extension of the principle to the whole sky under international auspices, and as the brothers Henri at Paris had recently successfully employed photography in the extension of the ecliptic charts so necessary for the identification of minor planets, the proposal was welcomed in France, and an international conference held at Paris in 1887, at which it was decided to construct a chart and catalogue of the whole of the sky, the catalogue to include stars down to the 11th magnitude, the charts to the 14th magnitude, each 2 degrees square, all to be taken with similar instruments and similar exposures, and the sky for this purpose to be divided into zones of declination, distributed among the cooperating observatories. The instrument of the brothers Henri was taken as the standard, of an aperture of 13 inches with a guiding telescope of 10 or 11 inches aperture. The distribution of zones was made with regard to the resources of the several observatories, and arrangements made to obtain fundamental observations of sufficient stars to secure the accurate reduction of the photographic observations. Thus to Greenwich Observatory was allotted the zone from the North Pole to a distance of 26 degrees from it, the authorities undertaking the actual taking of the plates, more than 1,000 in number, the accurate measurement of them, the production of copies, the publication of measures, and also the construction of a fundamental catalogue containing places of all the stars in the zone necessary for the determination of the plate constants. This catalogue forms the greater portion of the forthcoming 9-year catalogue, the result of a large number of observations made in the years 1897 to 1905. This is only one instance, different arrangements being made at different stations. For instance, in the case of the Oxford zone, the photographs were taken and measured at the University Observatory, Oxford, while the fundamental places were determined at the Cambridge Observatory, and the same zone is now being re-observed at Greenwich. Again, one measuring bureau deals with plates from both Sydney and Melbourne observatories, and successive conferences have had to deal with changes in the original plan caused by delay in those southern zones, rather rashly undertaken by observatories whose zeal outran their financial discretion. But the work is well advanced, most of the photographs are taken, and some of the volumes of results published. There is no room here for further reference to the various devices for measuring the plates and determining star places from them, but it seems quite likely, from a comparison made between plates taken at different observatories, that, owing to the slightly different adjustment of the various object glasses, the resulting survey may not be quite homogeneous. One of the many valuable contributions of the Harvard College Observatory and its able director, Professor E.C. Pickering, is a continuous systematic survey to the sixth magnitude, carried on almost automatically by means of a photographic telescope which exposes plate after plate to successive portions of the sky in series after series, the plates once developed being indexed and stowed away. Any question of an unfamiliar object, such as a new star, is at once referred to Harvard, where a series of plates of the region concerned, taken at different times for a long period, gives evidence of exactly the kind required. In the case of Nova Aurigay, for instance, several plates were found to have registered its image 6 weeks before its discovery. The Harvard College Observatory, with its southern outpost at Arequipa in Peru, is certainly an institution that astronomers could ill spare. Neither can they fail to appreciate the spirit in which its director, having had placed at his disposal for use in the most effective manner the projected Bruce 24-inch telescope, a great advance on anything of the kind at Harvard, resisted the temptation to have it installed there, and set it up in the purer air of Arequipa, where it could be applied to the comparatively neglected field of the southern sky. Since the middle of the century, catalogues of the old kind have been fairly numerous: Melbourne and the Cape, Greenwich, Armagh, the Radcliffe, Glasgow, and other observatories, contributing British catalogues, and American and continental institutions, also performing their share. But the growing importance of the photographic method has emphasized the necessity of a different sort of fundamental catalogue, on the lines of that of the British Association. Newcomb's Fundamental Catalogue of Standard Stars, published in 1899, is of this kind, embodying weighted mean results from all standard catalogues from Bradley's time, reduced to a common epoch by the employment of revised constants. Professor Auvers has projected a similar work for the epoch 1910, which, though completed, is at present almost inaccessible, while in 1903 Professor Louis Boss of Albany published another, in which he rejected the older observations of Bradley, Meyer, Piazzi, and Groombridge, as being of insufficient accuracy for his purpose. The new century saw a new project started in Germany to collect into one great catalogue the results of all known catalogues, some 300 in number, and as many observations as could be found not included in any catalogue, such as, for instance, those of Dr. Hornsby, an old Radcliffe observer at the end of the 18th century, and some of his successors, whose observations have never been published. This monumental work is being carried out under Dr. F. Ristenpart, and should prove of enormous value. The reobservation of catalogues is of extreme importance, especially after a long interval, and it not only enables corrections to be made to adopted values of precession, nutation, etc., but furnishes materials for the determination of apparent proper motion, from which can be found the motion of the solar system in space, and ultimately the actual proper motions of the stars. The distance between the several epochs being a factor entering directly into the question, it is obvious that in general the oldest reliable observations must be used for the purpose, and so for many years recurrence was had to Bradley's observations as the first point of measurement, but of late years the increasing accuracy of observed places tends to discount the necessity of a long interval between the epochs, and to enlarge the scope of the investigation to include fainter stars not observed until long after Bradley's time. Much valuable work of this kind was done by Auvers in connection with his re-reduction of Bradley's observations, and also by Porter of Cincinnati and Louis Boss. The first star found to have a really large proper motion was 61 Cygni, noted by Piazzi in 1792 as having an annual displacement large enough to carry it across a space equal to the Moon's diameter in less than 4 centuries. The next runaway, Groombridge 1830, first noted by Argelander in 1842, long held pride of place, requiring less than 3 centuries to cover the same space, but a much fainter star was discovered in 1897 by Kapteyn and Innis from the plates of the Cape Photographic Durchmusterung, to be moving at a pace that would do the distance in rather more than 2 centuries, and this star, under the appellation of Cordoba zones V243, is now the recognized champion sprinter, from the point of view of apparent motion. But it must be borne in mind that to deduce real from apparent motion, 2 more things are necessary in addition to the observed displacement. 1, the distance, is the objective of the hunt for stellar parallax. The other, the direction of motion, is perhaps not so obviously necessary, but it stands to reason that a star moving directly towards the solar system would show no cumulative displacement whatever in a century, however fast it moved, so that small proper motion is no actual criterion of small velocity. We have seen, however, that by means of the spectroscope, the velocity in the line of sight can be measured by the displacement of spectral lines, and by composition of the observed displacement at right angles to the line of sight, and the velocity indicated by the spectroscope in the line of sight, it is possible, if the distance be also known, to determine all the circumstances of the actual motion. It must suffice here to note that, so far as at present determined, the real velocities of the stars are in a very different order, Arcturus having an observed velocity of more than 250 miles per second, Groombridge 1830 being 100 miles per second slower, and the champion sprinter having less than a third of the velocity of Arcturus. These 3, numbered 1, 3, and 6 in order of tangential velocity, being respectively 21st, 2nd, and 1st in order of proper motion. The historic problem of stellar parallax is an application of the ordinary question in surveying, to determine the distance of an inaccessible object, with very strict limitations on the choice of a baseline and exceedingly small differences of angle to be measured, necessitating very great care and accuracy. The displacement of an object 5 miles away, viewed alternately with the right and left eye without moving the head, is greater than the parallax of any star. We have seen how many advances in astronomy are owed to the persistent search in this direction, from Bradley's discovery of aberration and nutation to Herschel's double stars, and how the genius of Fraunhofer at length provided optical means sufficient to enable Bessel to attack the problem with success. Since then, the number of accepted parallax determinations has steadily increased. Gill and Elkin, with the Cape heliometer, have shown the refinement possible in the way of precautions to avoid systematic error, and Gill's determination of the parallax of Alpha Centauri as 3/4 of a second of arc establishes that celebrated star as the nearest neighbor yet known to the solar system. The latest production in this field is a determination, under Elkin's direction at Yale, of 163 separate parallaxes, but the photographic method, introduced by Professor Pritchard at Oxford, has obvious advantages, and is gradually being adopted at Cambridge Observatory and elsewhere, though most of the well-determined large parallaxes are due to the heliometer in the hands of Gill, Elkin, Bruno Peter, and others. There is also a spectroscopic method by which the distance, in the case of binaries, can be inferred from the actual velocity from line-of-sight observations, and the orbital motion, or apparent angular velocity, allowing for the inclination of the orbital plane. A few years ago, while working on the reduction of the Cape Photographic Durchmusterung, Professor Kapteyn suggested a wholesale method of parallax hunting in connection with the Durchmusterung to be undertaken expressly for the purpose. A plate was to be exposed to each field in the sky at 3 successive maxima of parallactic displacement, and not developed until after the 3rd exposure, the interval between each exposure being naturally 6 months. Thus the first and last exposures would betray any cumulative effect such as proper motion, leaving the parallax to be determined directly by comparison of the second set of images with the mean of the other two. There are, however, considerable difficulties in carrying out this ingenious scheme, which has nevertheless been actually tried on a few plates. Changes in the film, however carefully kept, cannot be guaranteed not to take place. Moreover, it was found that the exact carrying out of the scheme involved in general exposures alternately east and west of the meridian, causing effects undistinguishable from those of a real parallax, so that to avoid these it was necessary to expose plates only on the meridian, and so to sacrifice the times of maximum displacement. There is no doubt, however, that some such plan is of great excellence in picking out stars whose parallax is large, so as to make a list of objects worth studying for the purpose. It was for a long time assumed, as a working hypothesis, that bright stars were nearer than faint ones, although this involved the tacit assumption of a most improbable actual equality in the stars. But parallax work on this line is disappointing, a far better criterion being apparent velocity. A faint star with a large proper motion is far more likely to show a measurable parallax than a much brighter star which does not show proper motion. The 7 apparently brightest stars in the heavens are Sirius, Canopus, Alpha Centauri, Vega, Capella, Arcturus, and Rigel, but of these, Sirius shows only half the parallax of Alpha Centauri, Vega and Capella barely a tenth, Arcturus only a 30th of the same amount, while Canopus and Rigel show none whatever. On the other hand, more than one star of the 7th magnitude or fainter shows nearly as great a parallax as Sirius. An obvious deduction is that so far from being even approximately equal, the stars cover an enormously wide range. Canopus must be at least 70 times as far away as Alpha Centauri, whose light reaches us in 52 months. It is inferred that Canopus gives more than 20,000 times the light of the Sun, while a star of 8.5 magnitude, also in the southern sky, turns out to be some 300 times less bright than the Sun, giving between these two stars a light ratio of 6 million. Still, the connection between brightness and distance is not entirely fallacious. It has been determined, by observations with the heliometers of Yale and the Cape, that the average parallax of stars of the first magnitude is 1/10 of a second of arc, corresponding to a distance of 33 light-years. Similarly, the average distance of second magnitude stars works out at 52 light-years, of third magnitude at 82 light-years, and so on, the ratio between the successive distances being about the same as it would be if all the stars had the same actual brightness, for the ratio of the brightness of one magnitude to the next is 2.512, whose logarithm is 0.4, so that the distance ratio would be the square root of this, 1.585, practically the same as the ratio of 33 to 52 or 52 to 82. It seems, however, from further investigations, that the average ratios are not the same in different parts of the sky, for instance in the Milky Way and far away from it, and also that they differ for stars of different types. The actual light received from all the stars is about 1% of the light of the full moon, and it has been proved that owing to the steadily increasing number of stars as we go lower in the scale of brightness, each successive class gives more light than the one before it. This has never been controverted, although it involves the apparent paradox that nearly all the light of the sky comes from the parts where no stars are visible to the naked eye. The difficulty is, of course, the confusion of the senses between quantity and intensity. 1,000,000 candles arranged uniformly in different directions at the same distance from an observer would be all separately invisible at a distance at which one light, of 1,000 candle power, would be conspicuous, though actually giving only 1,000th part of the light of the 1,000,000 candles. The increase of total light from each successive drop in the magnitude of the stars considered must have a limit, since otherwise there is a reductio ad absurdum, for the sum of an infinite series of increasing quantities must be infinite, and we might expect the whole sky to blaze with an overpowering brilliance against which the sun would be inconspicuous if not dark. There does seem to be a change in the ratio of increasing frequency of stars, somewhere below the 9th or 10th magnitude. Newcomb says at least the 11th, but it varies in different parts of the sky. If space were filled with equal bodies evenly distributed, the number of stars visible in any direction down to a particular magnitude would be about 4 times the number down to the next higher magnitude, but there is no known area where the ratio is so great as this. These considerations belong rather to stellar distribution than to photometry, but before fixing our attention on advances in that direction, it will be as well to emphasize some of the difficulties attending the approved numerical results of stellar analysis. The motion of the solar system in space has been already referred to as regards direction, and various determinations of the velocity, ranging from 14.5 to 10 miles a second, have ultimately yielded to a spectroscopic result of 12.5 miles per second. The spectroscopic inquiry into the actual direction will not be complete until the result of the D.O. Mills expedition to Santiago, Chile, to extend the investigation to southern stars is published. It is, however, probable that the final result for the apex will not be very far south of Vega, in conformity with a note in a previous chapter. The accompanying map from Kobold's Bau der Fixsternsystems shows how widely various estimates have differed. The velocity computed for most stars, for which results have been obtained, averages over 20 miles per second, so that our Sun is comparatively slow, but it has been computed that the whole universe cannot by gravitation control a velocity exceeding 25 miles per second, so that many stars headed by Arcturus with a velocity 10 times as great present anomalies whose explanation has hardly been attempted. Newcomb's figures, however, are not really based on the whole universe, which is an unknown quantity, but on the effect of 100 million suns, each of 5 times the mass of our own, distributed over a disk-like space of 30,000 light-years in extent. A spherical space of about 1/5 of this diameter, strewn with double the quantity of gravitating matter in the form of suns, would suffice, in Lord Kelvin's view, to produce velocities ordinarily met with among the stars. These estimates do not differ greatly from the hypothetical numbers suggested by a comparison of photographs for the total of the stars, 100 million having been actually mentioned as a fair estimate of the probable number that would be revealed by the greatest modern telescopes. The high velocities of Arcturus and other stars would seem to suggest a much greater quantity of unsuspected matter in the universe, possibly non-luminous or only faintly shining. Stellar photometry, however, though as we have seen the magnitude of a star is no actual criterion of its distance or size, is a branch of growing importance. After the time of Al-Sufi's catalogue, many ages elapsed before a catalogue appeared in which photometry was the chief feature. B.A. Gould's Uranometria Argentina, giving the magnitudes of over 8,000 stars visible at Cordoba, was published in 1879. A few years later appeared Pickering's Harvard photometry of more than 4,000 stars from observations with the meridian polarizing photometer, and Pritchard's Uranometria Nova Oxoniensis of nearly 3,000 stars visible to the naked eye from the North Pole to 10 degrees south of the equator, observed with the wedge photometer at the Oxford University Observatory. Both methods ultimately depend on the faculty of the human eye for detecting equality of light, the amount of rotation of the polarizer in the one case, and the thickness of the absorbing wedge in the other, to bring about the required diminution of the bright object, being the actual observation. The Harvard photometry has been extended southwards to the other pole by Professor Bailey's observations of nearly 8,000 southern stars at Arequipa, the southern outpost of Harvard College Observatory. Professor Pickering's more recent photometric Durchmusterung, from nearly 500,000 observations at Harvard, comprises photometric determinations of all stars down to the 7.5 magnitude between the North Pole and 40 degrees south declination. Small sources of uncertainty must always remain in visual estimates by various observers, and for the purposes of the astrographic chart, some method of photographic photometry was required. From among the uncertainties of definition and of plates, some general formulae have been extracted, giving a connection between the size of the image for a definite exposure and the photographic magnitude of the star, which, owing to the greater chemical action of the blue or violet rays, does not always agree with the visual magnitude. But the formulae are very irregular and inconsistent. Pickering's device of photographing two images of the same star, one direct and the other reduced by a screen, promises more consistent results. It is to be applied to a catalogue of 40,000 stars to the 10th magnitude, and a repetition of the determinations of the first Harvard photometry is promised by the new method in addition. The Draper catalogue has a spectrophotometric method, the intensity of a particular line being employed as the index for each star, but this is far from being a safe clue to either the visual or the photographic magnitude, especially for stars of varying types. Even to the eye, contrast of colors, the simplest evidence of varying type, renders photometric comparison difficult, but standardization of color has not made much progress, as the color perception varies in different individuals. The most important group of definitely colored stars is that of red stars, among which Ptolemy and others of the ancients appear to have included Sirius, which is certainly not red now. Footnote: Schiaparelli argues that the word used did not necessarily mean red, but simply bright. Footnote end. Al-Sufi, many centuries later, omitted Sirius, but included Algol, so even thus early there was evidence of color changes. Lalande in 1805 gave a list of 33 red stars. In 1866, Schellerup published a catalogue of 280 red stars, followed in 1876 by Birmingham with another containing 658 stars. Many of these are declared by Chambers to be rather orange than red, and it is certain that very few are of a deep red color. In 1888, Espin published a new edition of Birmingham's catalogue, with more than double the number of stars, adding also the spectral types to which they belonged, and 5 years later, Krüger of Kiel brought out a catalogue of more than 2,000 colored stars. Antares is the reddest of the bright stars, and is said to have derived its name from having been mistaken for red Mars. Anti equals instead of, Aries equals Mars. But most deep red stars are invisible to the naked eye, and a great number of them are variable and appear more orange at their brightest. There are many modern instances of changes of color like that ascribed to Sirius, including some which have apparently gone from red to blue. Ball's cursory parallax hunting at Dunsink, though unsatisfactory, supported the inference that red stars are not specially near our system, but they do seem to congregate in certain regions and to be often associated in pairs. This tendency is not confined to red stars, but is found in many groups in the sky, the late R.A. Proctor having collected evidence of what he called star drift in several regions, one including 5 of the 7 stars in the Plough. But one particularly interesting phase of color observations is associated with binary stars, the next subject that comes under our observation, postponing the general question of stellar distribution. End of chapter 28. Recording by Marvin Benarescu.
Chapter 29 of A History of Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marya James. A History of Astronomy by Walter W. Bryant. Chapter 29. double stars. Sir William Herschel's search for parallax resulted, as we have seen, in opening the field of double star astronomy and providing evidence to prove the extension of Newton's laws beyond the solar system. The field, once opened, was penetrated by Sir John Herschel and his friend South, and systematically explored by F.G.W. Struve, whose fame stands very high in double star astronomy. His Dorpat work was carried on after his departure by Mädler, and that at Pulkova by his son Otto Struve, whose double stars, though less than 1/4 as numerous as the 2,640 pairs ultimately catalogued by his father, include many difficult and interesting objects, one of which, Equali, has lately been proved to revolve more rapidly than any other acknowledged telescopic binary. In this case, as in some others, his discovery took the form of resolving one component of a previously recognized pair, thus forming a triple system. He was in the habit of applying to all his observations corrections of the nature of personal equation, depending on the separation and inclination to the vertical of the components observed, having experimented with artificial double stars in order to construct a table of corrections. This cautious principle seems to have been applied in his case with only partial success. Meanwhile, in England, after Sir J. Herschel's departure to the Cape, double star observers were not wanting, the best known being the eagle-eyed W.R. Dawes and William Smythe. In addition to searching for new pairs, old pairs were remeasured for the determination or improvement of their orbits, and to this branch Baron Dombowski of Milan devoted more than 1/4 of a century, while many names well known in other branches of astronomy will be found in the lists of those who have paid more or less attention to the measurement of double stars, as Bessel and Schiaparelli. About 1870, even Dawes thought that the field of double star discovery was nearly exhausted, though the gradual increase in optical power available seemed to hold out some promise of new ground to be broken. But the richness of the field still remaining was manifested without that aid, for in his spare time from 1871 to 1882, S.W. Burnham of Chicago, with a 6-inch telescope, discovered hundreds of new double stars. His marvelous powers soon found opportunity for work with larger telescopes, such as the 18.5-inch at Dearborn. Then from 1888 to 1892 he worked at the Lick Observatory, frequently using the great 36-inch for his observations, and was afterwards attracted to the new Yerkes Observatory of the Chicago University by the possibilities of the 40-inch. One of the first publications of the Yerkes Observatory was a collection of all known observations of Burnham's 1290 discoveries. The Lick telescope has not been idle, and with it W. J. Hussey and R. G. Aitken number their double star discoveries by the 100, as does G. W. Hugh of the Dearborn Observatory. T. J. J. C. at Flagstaff and R. T. A. Innes at the Cape met with similar success in southern fields, the latter having published a reference catalogue of southern double stars. One of the most important double star publications of the Lick Observatory, issued in 1901, was a complete catalogue and discussion of all the known observations of the pairs of Otto Struve. The system at Greenwich Observatory does not lend itself to the search for new pairs, but the much-needed reobservation of known pairs has been regularly prosecuted there since 1893, and more especially since the mounting of the 28-inch equatorial a year or two later, under the charge of T. Lewis, who, in addition to taking most of the observations for the first few years, and an important share afterwards, which still continues, has devoted himself for several years to the preparation of a full discussion of all the observations of Struve's 2,640 pairs, a great work which was published last year as a memoir by the Royal Astronomical Society. In this, as also in the Lick and Yerkes publications, much space is devoted to graphic determinations of the apparent orbits of stars which have been sufficiently observed to warrant it. And many interesting facts emerge from the discussion, one of which is to refute the old hypothesis that brightness and mass necessarily go together, for in many cases the mass of the fainter of two mutually revolving stars exceeds that of the brighter to a very marked extent, and even when this is not actually the case, the ratio of masses is out of all proportion with that of brightness. For instance, Burnham's close pair, 85 Pegasi, has a light ratio of 40:1 and a mass ratio of 1:6, while Procyon's companion, giving only 1/24,000th of the light, is 1/5 of the mass of its primary, the companion of Sirius showing a similar disproportion. These last two stars, Sirius and Procyon, the two dog stars, are remarkable instances of fulfillment of prediction based on the application of the Newtonian laws to the distant regions of the universe, for Bessel, who died too soon to see the fulfillment of his prophecy in regard to Neptune, also attributed the observed orbital motion of Sirius and Procyon to invisible companions. 6 years after his death, Dr. Peters deduced for the hypothetical companion of Sirius an orbit with a period of about 50 years, and in 1862, Alvin G. Clark, while testing an 18-inch objective in his father's workshop at Cambridgeport by setting it on Sirius, detected a faint star in the exact place computed by Professor Safford from Peters's theory. Auwers immediately upon this computed a period of 40 years for the hypothetical companion of Procyon, which was not discovered until 1896, when Professor Schaeberle caught sight of it with the Great Lick telescope. Struve calculated that between 2 and 3% of the stars down to the 9th magnitude are not single or 5% of the brighter ones, but later researches in this and other directions tend to show that the proportion is very much greater, though much of the evidence for this is spectroscopic and will be referred to in its own place. Struve also paid particular attention to color, and although in some cases difference of color seems to vary with the closeness of a pair in its orbit, in which case it can be attributed to an optical effect, yet in general it probably indicates different stages of development, and is a safer guide to difference in mass than the broken reed afforded by difference in brightness. Asaph Hall, the discoverer of Deimos and Phobos, also observed double stars with the Great Washington Telescope, as also did Barnard at the Lick and Yerkes observatories, but a list of prominent observers would be too long for a work of this kind. Not so long is the list of those who have done much work in computing orbits, including, in addition to those concerned in the recent discussions of Struve, Otto Struve, and Burnham stars, such double-star observers as Glazunov of Russia, Doberg of Hong Kong, and T.J.J.C., whose book on stellar systems, published in 1895, endeavors to trace the evolution of double stars on tidal principles analogous to those often postulated for the solar system. One pregnant suggestion made by Lewis in the great Struve memoir has a direct bearing on probable stellar distribution. He says the proportion of stars showing relative motion is in all probability much the same everywhere in space, so that if in any particular direction this does not seem to hold, the inference is not a change in the proportion, but an increase in the average distance in that direction, which prevents the detection of the proper number of relative motions, the limit of the resolving power of the telescope being directly dependent on the distance. Lewis infers that the Earth is not in the center of the visible universe. Another feature brought out clearly in the Struve memoir is the necessity, recognized long ago by Struve himself, of accurate observations with meridian instruments. The appeal to the Greenwich Transit Circle observations in the case of such a star as Psi Herculis brought evidence of the greatest value to the discussion of a system of more than two bodies, for which it was of importance to know the order of the masses, to which relative motions gave no clue. We need not consider multiple systems separately. An increasing number of so-called binaries are really multiple systems, As we have already noted in the case of delta equali, and to this case Epsilon Hydra, Psi Hercules, and many others belong, so much so that it is quite a usual artifice to account for apparently irregular orbital motions by the hypothesis of a close or faint companion to one or other of the components. The test of the common proper motion, applied to confirm or disprove the physical connection of a pair of stars, will not discriminate between what are usually understood by binary or multiple systems and what Proctor called star drift, except in cases where the proper motion is large, as for example 61 Cygni, which, though recognized as a double by Bradley, showed relative motion so little curved that even Burnham pronounced against the existence of physical connection. The evidence collected by Lewis in the Struve memoir seems conclusive, however, as to the actuality of the connection, though quite inadequate in a century and a half to determine the orbit. There is another class of binary stars in general quite distinct from so-called visual binaries. The Astronomy of the Invisible, whose study was commenced by Bessel, and to which we have already referred in connection with Sirius and other stars, is not the only direction in which the existence of bodies not actually seen can be inferred. The vast extension of the field of physical research made possible by the spectroscope, which we have already noted in connection with stellar motions and distances, again becomes prominent. There was no reason to suppose that Xi Pegasi, whose period of about 11 years until Hussey's recent research into the orbit of delta equali was long considered the shortest of any known binary, really represented the lowest limit in the universe. Twin suns, so far as any evidence could possibly be adduced, might revolve much closer together than any system that could be separated in even the largest telescope, and as a case in point, the demon star of the Arabs, Algol, was regarded as an eclipsing binary, and its period of less than 3 days indicated a proximity out of all proportion with those of stars whose revolutions are measured in years. Confirmation of the theory of Algol was forthcoming as soon as the line of sight velocity was investigated by Professor Vogel, showing motion alternately towards and from the observer in a single bright body, periodically dimmed but otherwise unaltered in quality of light, proving that the revolution of two bodies, one dark, suggested by Goodricke in 1783, did actually take place so nearly in the plane passing through the earth that the bright body suffered partial eclipse at each revolution. This evidence, produced in 1889, was not the first example of a star being proved double by the spectroscope. Dr. Henry Draper, whose work in solar spectroscopy has already been noted, commenced a spectroscopic investigation of stars, cut short by his death in 1882. But in 1886, the Draper Memorial work was commenced at Harvard College Observatory under Professor Pickering, with instruments and funds provided by Mrs. Draper, and its first publication, which appeared in 1890, took the form of a catalogue of the spectra of the brighter stars in the northern hemisphere. The second Draper catalogue was to contain the spectra of 30,000 stars in both hemispheres, the instrument used at Harvard having been sent to Arequipa in 1889 to secure uniformity of results. The work of measurement and discussion was in the hands of a staff of ladies under Mrs. Fleming, and it was found on comparing several spectrograms of the brighter component of Mizar, Psi Ursa Majoris, the middle star in the tail of the Great Bear, or the horse on which the wagoner rides in charge of Charles's Wain, that two of them, taken in 1887 and 1889, showed the K-line double. Professor Pickering announced this discovery, indicating his conclusion that the evidence pointed to the star being double. He entrusted Miss Antonia C. Maury, a niece of Dr. Draper, with the examination of 70 spectrograms, which showed that the other lines in the spectrum were also affected. It seemed then that two nearly equal bodies mutually revolved in a plane not greatly inclined to the line of sight, and that the doubling of the lines must indicate velocities in opposite directions in the line of sight, while the single-line spectrograms would correspond to times when the motions, though still, of course, in opposite directions, were practically across the line of sight, betraying no measurable radial velocity. This was the first discovered spectroscopic binary, though the principle employed had been suggested for investigation, though not for discovery, by Fox Talbot in 1871. Miss Maury worked out an apparent period of 52 days between successive widenings, indicating a period of revolution of 104 days, but this has been reduced by Vogel in 1901 to rather under 21 days, the uncertainty being due to an orbit far from circular. Footnote. Curiously enough, Mizar was also the first recognized visual double star, having been noted at Bologna by Riccoli in 1650, and also the first photographed as such by G.P. Bond in 1857. Moreover, there is every probability that Mizar with Alcor was the first, as it is certainly the best known naked-eye double star, the names having been given by the Arabs. In 1889, Miss Maury detected a 4-day period in Beta Aurigae, which thus ranks as the second discovery of the new class. It has been computed by Huggins that this binary could not have been discovered visually, as to separate the components would require a telescope of 80 feet aperture. In 1890, Vogel added another, Spica, to the list, but in this case the duplicity was betrayed not by the doubling of the lines, for the companion appears to be dark or too faint to show a spectrum, but by their oscillation, denoting motion alternately towards and from the Earth. Both components of Castor appear to be spectroscopic binaries, the fainter one announced by Belopolsky of Pulkova in 1896, the other recently by H. D. Curtis of Lick Observatory. In 1899, Capella, almost the brightest star in the northern hemisphere, was simultaneously announced by W. W. Campbell of the Lick Observatory and H. F. Newell at Cambridge to be a spectroscopic binary with a period of 104 days. The components appeared to be probably not very unequal in brightness, and, the parallax being known to be sensible, it was computed that the apparent angular distance might be not much less than 1/10 of a second of arc, so there seemed a possibility that the star might prove to be a connecting link between visual and spectroscopic binaries, and it was carefully scrutinized with some of the most powerful telescopes. The Lick telescope betrayed nothing, the image appearing quite round at all times, but the Greenwich 28-inch, having its object glass adjusted for a different part of the spectrum, yielded a more promising result. And though many of the observations published are probably worthless and may be ascribed to optical or psychological causes and to want of experience in judging of the suitability of observing conditions for what was practically a unique observation, yet there is little doubt that a certain proportion of the observations can be regarded as genuine. The mean resulting period from several revolutions in successive years comes out persistently between 103 and 104 days, the spectroscopic determination being exactly 104 days, and the discordance seems to suggest a motion of the apse line of the orbit of Capella, of which the spectroscopic observations would take no cognizance. No other instance is yet known of a spectroscopic binary affording much chance of visual confirmation, though a period of about 3 years in Beta Capricorni, for instance, is a promising sign. The number of recognized stars of the new class is steadily increasing as the determination of velocities in the line of sight reveals more and more instances in which that velocity is variable, indicating orbital motion. By the end of 1904, the number had reached 140, most of them being of the same character as Spica, the second star in point of brightness, being dark or very faint. These 140 stars, with 4 others discovered after January 1st, 1905, are given in the first catalogue of spectroscopic binaries issued by the Lick Observatory in 1905. When we bear in mind that the probably large number of binaries whose motion is nearly at right angles to the line of sight cannot be detected by this method, it is not difficult to see how far from rare is the occurrence of physical pairs. End of chapter 29.
Chapter 30 of A History of Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Daniel Wolfe. A History of Astronomy by Walter W. Bryant. Chapter 30, Variable Stars. We have noted the gradual widening of the field of variable star observation, from the isolated new stars of Hipparchus and Tycho Brahe to the discovery of variables of long and short periods, of Mira, of Algol, and of the anomalous Eta Argus, and incidentally remarked on the binary character of eclipsing variables like Algol, indicating the spectroscope as a valuable aid in this as in other fields of investigation. It must suffice for the earlier period, when this branch was of very slight importance, to note that the increase in photometric accuracy realized by Argelander in preparing the Bond-Durchmusterung, in all cases insisting on grading not in magnitudes but in tenths of magnitude, was responsible for the quicker recognition of smaller variations hitherto unnoticed, and, indirectly, for the attraction of many enthusiastic workers into a field suddenly become one of great promise, and not requiring necessarily great optical power. It was not until 1880 that Pickering published a classification of variables, according as their variation is 1. Non-periodic, 2. Great and slow, 3. Irregular, 4. Quick and in general small, or 5. Of an eclipse character. It has been claimed that the evidence collected by J. E. Gore of slow secular change demands a new class, but it is doubtful if any star in the universe can be considered as absolutely invariable, and a star that shows a small diminution of luster in a period of many years, sometimes of centuries, may after all turn out to be periodic. On the other hand, others, on the ground that variables ought to be restricted to periodic variables, object to the inclusion even of new stars, the chief members of Pickering's first division, and might similarly object to some members of the third class. The truth is that it is, as usual, hard to draw the line of exclusion or even of classification. The first class should include, besides new stars, such as those of Hipparchus, Tycho Brahe, and Kepler, also what are called lost stars, of which there are some authentic instances. Failure to reobserve a few stars found in old catalogues may occasionally be explained in other ways, some being traced to then undiscovered planets, some to observation errors, such as a wrong hour for right ascension, or mistake of 10 degrees in circle reading, a wrong sign of declination, or other errors of transcription. But it does occasionally happen that an undoubted star, such as 55 Hercules, is no longer to be seen, and must be relegated to the temporary class. Tycho's nova, for a time as bright as Venus and visible in daylight, was the brightest of this class. That of Kepler in 1604, estimated at its maximum equal to Jupiter, being followed by a very long period without such a phenomenon. It is possible that a small star still visible marks the place of Tycho's Nova Cassiopeia, 1572. A characteristic of stars of this type is the sudden increase in brightness compared with the slow fading away. The nova of 1572 increased for about a month from discovery and faded for 5 months before being invisible to the naked eye. That of 1604 reached its maximum in a few days, remained very bright for a month or more, and was visible to the naked eye for more than a year, disappearing early in 1606. Both these, of course, appeared before the invention of the telescope. Nova Corona, discovered by Birmingham in 1866, reached the second magnitude very quickly, fading also rather quickly. It was called T Corona according to the convention by which all variable stars discovered in a constellation, unless already provided with names, are assigned the generic name of the constellation prefixed by successive capital letters from R to Z. After 9 have been appropriated in the same constellation, the same process is applied as in the case of minor planets, except that only the same 9 letters are used, so that UY Cygni, for instance, is the 8th of the 5th series, or the 44th name thus allotted to a variable in that constellation. T Corona was the first nova examined through the spectroscope, and the appearance presented to Huggins was of 2 spectra, one similar to that of the Sun, the other superposed upon it of 5 bright lines, attributed to incandescent hydrogen. Nova Aurigæ, discovered early in 1892 by Rev. T. D. Anderson of Edinburgh, was proved to have been visible more than a month earlier by reference to the Harvard photographs. It remained visible for a longer time, enabling continuous study of its spectrum to be made, and even after fading beyond the reach of all but the greatest telescopes, brightened up to the 9th magnitude and continued to fluctuate for about a year longer before again fading into insignificance. At first, the spectrum was double, as in the case of T Corona, and the deduction from it at first was the presence of two bodies, one approaching the Sun with a velocity of about 500 miles per second, and the other receding at about 250 miles per second, according to the gaseous hydrogen lines, or 150 miles according to the calcium lines. The hypothesis of a grazing collision between two bodies thus inferred has not been substantiated. After fading, the spectrum appeared faint and continuous with a green nebular line, subsequently resuming a stellar appearance. Mrs. Fleming claimed 5 nova detected on Harvard photographs before the end of the century, but the new century had not long commenced when the discoverer of Nova Aurigæ obtained a more striking success by the recognition of a new object in Perseus, which is attributed generally to him, though possibly seen earlier by a Russian student at Kiev. 2 days before discovery, it was invisible on a Harvard photograph showing stars to the 11th magnitude, but almost immediately after discovery it was rather brighter than Capella, much brighter than any nova since that of Kepler nearly 300 years before. During its fading, it brightened regularly about every 3 days for some time, and owing to its having been discovered some days before its maximum, the spectroscopic indications of its character were not at first of the normal type. It went through the usual series of changes, afterwards appearing as a planetary nebula on its way to become an ordinary star again after the lapse of a few years, taking 3 years to reach the 10th magnitude. But it had one unique feature in the form of a nebulosity surrounding it, actually shown on a photograph taken with the Crossley reflector at the Lick Observatory within 6 weeks of its appearance, but not noticed until some months later. Messrs. Flammarion and Antoniadi announced 6 months after the discovery of the nova that it exhibited a nebulous aureole. Dr. Max Wolf at Heidelberg, while attributing the aureole to the peculiar character of the light, noticed on one of his photographs a strong trace of nebulosity some distance to the south, and suggested a photographic test with the great American instruments. Perrine at Lick Observatory and Ritchie at Yerkes Observatory then obtained photographs showing a growing nebulosity in the form of a series of spirals, apparently spinning from the nova and spreading outwards at the rate of 11 minutes of arc in a year, which, by comparison with the earlier Lick photograph, seemed to have started some days before the original outburst of light. As no parallax had been detected, this involved velocity of motion so enormous as to be quite incredible on the ordinary supposition that the nebulous matter was being ejected by the nova. It was suggested by Kapteyn and Seeliger and others that the nebulosity was there all the time, but was becoming visible as the light from the nova reached each successive convolution, and though the light showed no polarization, so that it did not seem to be reflected light, yet some such velocity as that of light, far transcending any imaginable motions of particles, seemed requisite to account for the rapid growth of the nebulous appearance. The velocity of light would suffice at a distance corresponding to a parallax of 12,000ths of a second of arc, and very careful measures suggested a small parallax not far from that value. We may then tentatively attribute the phenomenon to electrical or other excitement propagated outwards from the center, with a velocity something like that of light, rendering successive portions visible. F. W. Very considered that actual emission of particles by electrical repulsion or light pressure might possibly take place at a sufficient rate to explain the phenomenon, and the question cannot be regarded as settled. An example of the accidental factor in discovery was afforded in the case of Nova Geminorum 1903. Professor Turner, director of the Oxford University Observatory, picked up an astrographic plate put aside as rejected. On inquiring the reason, as the plate appeared perfectly good, he was informed wrong setting, the usual cause of such being an accidental error in reading one of the setting circles by which the observer views a wrong field, and consequently picks up a wrong guiding star. Further inquiry, however, showed that this was not the usual case, but that the intended guiding star had been put out of countenance by a brighter one not far off, which had naturally caught the observer's eye. But no brighter one was indicated there in the zone catalogue, and it turned out that the guiding had been done by means of a nova. The original idea that the appearance of these temporary stars must be attributed to a collision between two more or less solid bodies, or one solid body and a fairly condensed nebula, is gradually being abandoned, since, of the several successive different phases shown in the spectrum of a nova until it reaches the stage of a faint star again, there is not one that necessarily denotes instability. Even the characteristic spectrum associated with a nova, not reached the first day or two after discovery in the case of Nova Persei, is seen permanently now in the celebrated Eta Argus, and other stages belong to well-known spectral types, of which there are hundreds of examples in the sky. Of periodic variables, the number announced is rapidly increasing, though the determination of periods and light curves is a slower process. Chandler's first catalogue of variables, appearing about 1888, contained more than 200 stars. His third, in 1896, contained nearly twice as many, and as he found too little time to complete his fourth, the work has been undertaken on a much more extensive scale by the German Astronomical Society Astronomische Gesellschaft. Meanwhile, however, in 1903, the Harvard Provisional Catalogue with supplement included more than 1,300. 400 were detected at Harvard alone in 1904 from comparison of photographs, more than half of them in the two Magellanic Clouds, and nearly a quarter in the Orion Nebula, followed next year by more than 800 in the smaller Magellanic Cloud. In the same 2 years, practically 400 variables were officially numbered as authentic. By far, the greater number of long-period variables have periods of 250 to 400 days. The first known, Mira Ceti, varying from 2nd to 10th magnitude in about 11 months. Chi Cygni varies from 4.5 to 13.5 magnitude in 13.5 months. V Delphini from 7.3 to 17.3 in 540 days. This is the widest range of magnitude known, corresponding to an actual brightness ratio of unity to 10,000. Mira, however, though its range is about 8 magnitudes, sometimes rises to a higher maximum than usual, and sometimes sinks to a lower minimum. This irregularity in degree seems not so strange as it would be in the case of an eclipsing variable, for the spectroscopic evidence goes to show that each brightening is of the nature of a fresh outburst of activity in the form of blazing hydrogen. There seems no periodicity in the high maxima, unless we accept one of 59.5 years suggested by P. Guthnick, and the light does not invariably follow the usual rule of a rise quicker than the fall in brightness. Moreover, on one occasion the maximum was a month late, while minor deviations from the mean period are not unusual. These irregularities point to an analogy with the sunspot period, though on a very much exaggerated scale. Chi Cygni is even more irregular and has also a greater range of magnitude. Its average period has been lengthening slowly ever since its discovery in the 17th century, and is now 1% longer than it was. Some of these stars show well-marked double maxima, and some are only regular in the fact of their alterations, no similarity showing itself between successive ranges of variation. Aurigae was supposed to be quite irregular, though only slightly variable, until in 1903, Dr. Ludendorff of Potsdam got out a period of just over 27 years, far longer than that of any other known variable. The most irregular variable known is beyond question Eta Argus, more generally known since the subdivision of that great constellation as Eta Carina, to which we have alluded before as now showing the typical spectrum of a nova. It is supposed to have been fainter than the 4th magnitude in Ptolemy's time, as he did not record it, though others at the same altitude at Alexandria are found in the Almagest. Halley, in 1677, at St. Helena, obtained the first known observation of it, assigning to it the 4th magnitude. 10 years later, and again to Lacaille in 1751, it was of the 2nd magnitude. The variation since more regular observations began is shown in the accompanying diagram, showing that for some time, nearly 10 years in fact, it was brighter than any star in the sky except Sirius, but has been invisible to the naked eye since 1868, and now shows a dull red in the telescope with no apparent variation at all. Red stars show a large proportion of variables, and nearly all long-period variables are red, so that there seems some connection between the two characteristics. A. Safarik of Prague, from 5 years' observation, 1883 to 1888, of a list of 22 red stars, found 8 variable and 5 more or less dying, whose loss of light was confirmed from previous observations. A few cases are, however, known of red stars growing brighter and remaining so. Of the variables of short period, generally taken to mean those of period less than a month, by far the greater number go through their cycle of change in less than 8 days, and a fair portion in less than 1 day. All of them seem to be close binary systems revolving in the period of variation like the eclipsing variables of the algal type, but the changes in Pickering's 4th class are not due to eclipse. They are sometimes divided into 3 subordinate classes, the first of which, Delta Cephei, is a type containing stars showing no tendency to stay at maximum or minimum, their rise being, however, about twice as quick as their fall in luminosity. Spectroscopic evidence suggests in every case tested the presence of a dark or faint companion. In fact, all appear to be spectroscopic binaries. A recent suggestion of Dr. Marvin in 1905 to account for the variation of Delta Cephei is that the orbit is eccentric, and the light change due to a change in radiation depending on the distance. The second subdivision, cluster variables, includes those hundreds noted at Harvard and the Magellanic Clouds, and very few are found outside clusters in the open sky. They generally show periods of less than a day, with a very sudden rise to maximum, a much slower return, and stronger tendency to stay at minimum. Y Lyrae, discovered by A. Stanley Williams in the northern hemisphere, and S. Array by R. T. A. Innes in the southern, are very similar typical cases. In 1904, Madame Swarovski discovered a cluster variable in Cygnus with a computed period of only 3 hours 12 minutes. In the previous year, a period of about 4 hours for a star in Ursa Major had been claimed as the shortest known, only 3 stars having shown variations half so quick. Zeta Geminorum, the main type of the remaining subdivision, is a spectroscopic binary discovered independently by Bela Pawlowski and Campbell in 1898. But though the companion is a dark body, the minimum does not occur at conjunction, and is therefore not due to eclipse. The feature of this class is the regularity of their rise and fall, though one, S. Antillae, one of the 3 referred to in the last paragraph, having a period under 8 hours, shows a marked tendency to remain at maximum, and so was for some time regarded as an algol variable. The best known variable in the group is Beta Lyrae, one of several instances of a sort of double periodicity, equal maxima being separated by alternate unequal minima, suggesting that the appearance may be caused similarly to that of an algol variables, except that in this case the bodies, though unequal, are both bright, so that each alternately occults the other. On this hypothesis, Professor G. W. Myers concludes that the smaller body is the brighter, the low minimum occurring while it is behind the larger body, the higher one when it passes in front. He also accounts for the regularity of the changes by assuming a gaseous constitution for the bodies, which are supposed to revolve almost in contact, so that by mutual attraction they are elongated. Thus, the maxima occur at times when there is no foreshortening, whose effect, as they rotate, is to cause a steady diminution of light until conjunction. A similar case, U Pegasi, Myers considers an example of recent investigations of Pensier and Darwin on possible figures of equilibrium for revolving masses of fluid, one of which, called apoidal or B-shaped, is that of 2 masses in actual contact. It is this hourglass form that Myers suggests for U Pegasi. On the assumption that Myers is right, these stars might be relegated to the algol class, as they would owe their principal loss of light to eclipse. Professor Newcomb suggests distinguishing between stars whose variation depends on the direction of the line of sight, and those independent of it. All algol variables would cease to be variables if the line of sight were perpendicular to their orbital planes. So would Beta Lyrae and U Pegasi, according to Myers. It is very difficult to draw a line, especially as the suggested explanation may not be correct. In the case of Y Cygni, discovered by Chandler in 1886, with a period long uncertain owing to its commensurability with daylight, a suspected period of 1.5 days being difficult to verify as alternate minima would be invisible, ultimately showed a variation in 3 days with 2 unequal portions of 33 hours and 39 hours respectively, indicating an eccentric orbit not bisected by the line of sight. All such stars as these would be certainly regarded as algol binaries by A. W. Roberts of Lovedale, South Africa, one of the leading workers in the southern hemisphere at this branch of astronomy. He distinguishes no less than 5 types of algol variation, one of which, R2 Centauri, is almost a model for U Pegasi, and claimed as an apoidal binary. It is evident that a dark component is not universally considered essential for an algol variable. Roberts obtained separate curves according to the relative size and brightness of the 2 components. The longest period known for an algol binary is just over 31 days, in the case of UZ Cygni, discovered by Mrs. Fleming in 1902, which she considers probably an apoidal system. 3 years later, this discovery was followed in the same place by that of W2 Tauri, whose variation from approximately the 7th to the 11th magnitude is the greatest of any algol-type star. Notwithstanding the range, which in a long-period binary increases more or less with the period, this star, like all but 2 of the algol group, goes through its changes in less than 5 days, as a matter of fact in about 2 3/4 days. H. N. Russell of Princeton and A. W. Roberts, from different data, found the average density of algol variables much less than that of the Sun, and their spectral characteristics also differentiate them from ordinary short-period variables, which are of the solar type. Variable stars do not appear to be near the Earth. Mira has a proper motion of 1/4 second of arc annually, but the only parallax determined by Dr. Chase makes Algol 10 times as distant as Sirius, or nearly 90 light-years away. Like the closely allied red stars, many of which are variable, they seem gregarious, as besides the class of cluster variables, several are found near the positions of various novae, indicating that certain regions of space are far more favorable to variation. The best-known observers of variable stars in this country are Stanley Williams, Anderson, and Gore, the British Astronomical Association also doing good work under the direction of Colonel Markwick. Elsewhere, W. Swarovski and his wife in Moscow, Roberts in South Africa, and a large number of Americans have devoted themselves to the work, including J.A. and H.M. Parkhurst, E.F. Sawyer, and P.S. Yendall, in addition to the Harvard band under Professor Pickering and Mrs. Fleming, whose investigations are mostly photographic. We have already referred to S.C. Chandler's work in forming a catalogue, now in the hands of Dünner, Mueller, and Hartwig. A very valuable contribution to the subject is Father Hagen's Atlas Stellarium Variabilium, which is in constant demand among those who do the necessary work of carrying out a series of observations of recognized variables in order to confirm or improve the periods and light curves. The latest catalogue, the second Harvard Catalogue of Variable Stars, contains 1,791 variable stars in the Magellanic Clouds and 1,957 elsewhere, showing the enormous recent progress now being made in this subject. End of Chapter 30.
Chapter 31 of A History of Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A History of Astronomy by Walter W. Bryant. Chapter 31. Clusters, Nebulae, Milky Way. The history of research among clusters and nebulae is to a great extent that of improvements in photography. It is impossible to dwell in any great detail on the manifold varieties among the thousands of objects indexed in Dreyer's General Catalogue of Nebulae and Clusters, enlarged and revised from that of Sir John Herschel, and continuing with supplement nearly double the number of Herschel's 5,000, indicating the progress in 30 years from the publication of the one in 1864 to the completion of the other with its supplement between 1888 and 1894. The Herschels considered nebulae a distinct class, but the Earl of Rosse, in the heyday of his great Parsonstown reflector, resolved so many apparent nebulae into clusters that an opinion gained very general support that all nebulae could be similarly resolved. The year of publication of Herschel's catalogue saw the vindication of their older theory, for Huggins then turned his spectroscope towards a nebula and found instant evidence from its bright-line spectrum that it was no group of stars, but a mass of incandescent gases, which appeared to him to be hydrogen and nitrogen. Many other nebulae gave similar results, though the line attributed by him to hydrogen and by Lockyer to magnesium had ultimately proved to belong to an unknown substance, to which the name nebulium was given, just as helium had been assigned to the chromospheric substance responsible for the D3 line. In many nebulae, the gas may be under pressure, as they show a continuous spectrum, or they may after all be more similar to clusters, many of which also yield a continuous spectrum. Helium itself is found in some of the nebulae. Clusters seem to suggest universes in being, just as nebulae may be taken to represent them in the making. But there is a marked difference between such a group as the Pleiades, in many ways the most remarkable collection of stars in the sky, and the globular cluster of which Omega Centauri is an excellent example. The Pleiades, whose rising and setting rule the agricultural calendar of several distinct primitive nations, and which have been by others taken to be the abode of the gods, and more recently regarded as possibly the center of the universe, the brightest star, Alcyone, has been suggested as the central sun, are certainly an irregular cluster. Bessel's triangulation of the group, 1829 to 1841, repeated by Gould a quarter century later from a photograph by Rutherford, and very carefully by Elkin at Yale in 1884 and 85, shows that of the 50 brightest stars in the group, only 6 do not appear physically connected with it. The rest have a common apparent proper motion, almost entirely due to the motion of the sun in space, and are consequently inferred to be at a vast distance from the Earth, so that every one of the 40-odd stars is brighter than the sun, and the brightest of them probably 170 times as bright. Subsequent estimations by Pickering and Stratonoff now show that not only 6 stars above differentiated, but most of the fainter stars also are at an enormously greater distance and do not belong to the system. it is impossible to obtain just appreciation of the conditions in such a system as compared with our own, the dimensions being out of all proportion. Possibly, the feature best worth recording is the extraordinary ramifications of nebulosity, in which the stars seem to be involved, the detection of which is one of the triumphs of celestial photography. Some faint indications of a globular form have been claimed even for the Pleiades, but it is unmistakable in Omega Centauri, other clusters appearing elliptical, triangular, or fan-shaped, and many groups of the stars and clusters showing apparently closer physical connection, in some cases like beads on a string of nebulosity. In an area around Omega Centauri, less than twice that covered by the full moon, more than 6,000 stars have been photographed, of which 3/4 appear to belong to the system and 125 to be variable. A much smaller cluster, 47 Tucanae, shows even more stars. Moreover, as a rule, the arrangement of stars in a cluster does not seem to be quite haphazard. For instance, in some, the brighter stars seem to represent crooked spokes, while the fainter ones crowd into the center. It seems very possible that clusters represent condensation from nebula. Globular clusters show no true nebulosity. The Pleiades may correspond to one intermediate stage, and various other forms to other stages. Perhaps someday the spectroscope may enlighten us further as to the possible processes of evolution. Meanwhile, the nebulae themselves show numerous gradations. The first catalogue of nebulous objects, many of them clusters beyond the resolving power then available, were produced in 1781 by Messier, the ferret of comets of Louis XV, who hoped for providing a list of such spurious comets to save himself some proportion of his frequent disappointments. The very names of many of the better-known nebulae, the Ring Nebula in Lyra, the Crab, the Dumbbell, the Keyhole, the Fishmouth, the Spider, the America Nebula in Cygnus, and the Whirlpool Messier 51 in Canes Vernadisi, indicate greater diversities of apparent shape, but other differences are more important. Nebulous stars, surrounded by a sort of glow of nebulosity, may be only prospective variants of stars of nebulous appendages of various forms, and at least one of Herschel's nebulous stars is really a close spiral. Planetary nebulae, whose uniform brightness almost persuaded Herschel to discard them, have generally stellar nuclei also, and one of them betrays a sort of spiral form. In fact, almost every kind of nebulae seems to hint at some stage of the same development. Apart from photography, the amount of work done in recent years is not great. Lewis Swift, a well-known comet discoverer, devoted a considerable time to the successful search for new nebulae, and G. Begorden of the Paris Observatory has performed a very troublesome task in determining accurately the positions of hundreds of these objects, publishing a catalogue of nebulae and clusters in 1899. Since 1880, when Draper photographed the Orion Nebula, many refracting telescopes, whose special advantages for the recording of faint nebulosity render them much more suitable for the purpose than refractors, have been employed in similar work. In 1883, Dr. A. Common of Ealing obtained with his very large reflector a very fine photograph of the Orion Nebula, for which he received the gold medal of the Royal Astronomical Society. In 1885, Dr. Isaac Roberts began to devote himself to the task, and by the end of the century had published 2 volumes of splendid photographs, also receiving the gold medal. Max Wolf at Heidelberg and Bernard and W. H. Pickering in America worked in this same field, the former publishing in 1902 a catalogue of about 1,500 nebulae north of the Milky Way. The most striking success was achieved by Keeler with the Crossley reflector at the Lick Observatory. This was a 3-foot instrument made by Calver for Dr. Common, from whom it was purchased by Mr. Crossley, a Yorkshire merchant, who, finding the atmosphere of Halifax quite unsuitable for so large an instrument, presented it to the Lick Observatory, where it was for some time almost ignored, one and another finding it unsuitable for various purposes. On the appointment of J. E. Keeler to the directorship in 1898, he at once justified his election by undertaking to work himself with the despised instrument, over which friction had arisen, and with rare intuition devoted it to nebular photography with such success that in the 2 years left to him, he died in 1900, he not only found nebulae so thickly strewn in his photographs that he estimated the number in the sky within reach of his instrument at about 20 times the number already known, inferring a total exceeding 100,000, 500,000 has since been suggested by Professor Bryant, but also came to the conclusion that at least half of them are spiral, and from this produced the germ of the planetesimal hypothesis. This idea, to which reference has already been made, does not concern itself with the genesis of nebulae from the protoplasmal material by condensation of gases or collisions of meteoric dust, but does endeavor to generalize the subsequent development of all nebulae in a manner not at variance with a plausible history of the evolution of the solar system from its supposed primitive nebula. Professor F.R. Moulton starts afresh from the mathematical point of view with a more or less spheroidal nebula, rejecting as necessary Laplace's assumed high temperature, in the light of modern researches into the mechanical production of heat and conservation of energy. Two such bodies in rotation traversing paths approaching near to each other will be subjected to powerful tidal effects, whose effect will be to elongate them towards and from each other, and the suddenness of the strain on the bodies loosely coherent might readily cause disruption of a portion at the end of a diameter. The relatively lower velocity of these fragments will cause them to leave the parent body in a spiral direction, dragging after them wisps of uncondensed material. The continuation of this process, so long as the bodies are near enough together, is supposed to ultimately leave a central nebula with spiral arms knotted at regular intervals with more condensed masses, all rotating and gathering up the remnants of nebulosity. The evolution from this of a globular cluster differs only in dimensions from that suggested by Moulton and Chamberlain for the solar system. We cannot yet refer to all systems apparent in the sky to stages in this hypothesis, which is sufficiently suggestive to meet with provisional approval. It may be that the more condensed planetary nebulae have been too solitary to conform to pattern, and the double stars represent cases where approach has been too near to allow of recession. It may be that the nebulosity around Nova Persei is an imperfect sketch, showing the spiraliform in non-luminous matter, revealed in some way by the light change in the central condensation. There is plenty of scope for interesting speculation in the attempt to harmonize every apparently unique phenomenon with the resistless workings of a universal law. But the hypothesis has not reached the status of Newton's law of gravitation, and may, after all, meet the fate of his dynamical theory of light. The source of the original energy is yet to seek through physical research into the possibilities of radioactivity may supply a clue. The Milky Way, stretching with hardly a break all around the heavens, though for some distances divided into two branches, suggests an obvious plane of reference in celestial distribution, and one of the first theories of the universe, the grindstone theory of Thomas Wright of Durham, 1750, assumes that the condensation of stars in that region indicates the shape of the universe, our system being supposed to lie in the interior of a disk-like aggregation of separate bodies, which naturally appear more thickly strewn in the plane of the disk. Kant's idea involved a plurality of such systems, regarding nebulae as island universes, each with its own Milky Way. Newcomb's counting of stars in various regions pointed to the result that the fainter the stars considered the greater is their crowding in the Milky Way compared with the rest of the sky. Moreover, gaseous nebulae, novae, and stars of certain spectral types, in general, the more photographically bright stars, appear more frequently in the Milky Way than elsewhere. The conclusion that the galactic plane denotes the direction of greatest extension of our universe is almost inevitable. At the same time, analysis to proper motions suggests to A.S. Eddington at least two distinct universes, so to speak, moving in different directions. A similar idea appeared before in the guise of a suggestion from Gill and Kapteyn that the brighter stars as a whole showed rotation with regard to the fainter ones, but it apparently broke down under further analysis. It is difficult to reconcile our ideas of gravitation with interlacing and yet independent motions, but suggestions have been thrown out to the effect that such systems might persist at different distances, so that one moved wholly within the other in a manner analogous with the idea of rotation of the brighter stars, still presumed in the mean to be the nearer stars. Or again, it is hinted, the case may be met by assuming for our system a position well outside the center of a single universe, so that a fair proportion of its members, by virtue of their position, like planets at the inferior conjunction, would appear to be moving in a different direction to the rest. End of Chapter 31.
Chapter 32 of A History of Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in November 2020. A History of Astronomy by Walter W. Bryant. Chapter 32. Stellar Spectroscopy. A full account of the growth of stellar spectroscopy would take us too far from the purpose of this little book, and it is not easy to find a suitable place to consider it as a whole. It has been necessary to refer to spectroscopic inquiries in connection with various problems, and to quote such matters as spectral types, which should perhaps have been explained in an earlier chapter. It seems advisable to deal briefly with this matter in a separate chapter, instead of overloading the text with footnotes. We may here repeat the elementary propositions implied in our notices of solar spectroscopy. A continuous spectrum infers incandescence of a body, either solid or divided into solid particles, or gaseous if non-transparent. A spectrum of bright lines denotes an incandescent gaseous transparent mass. If an incandescent body is surrounded by a cooler gaseous atmosphere, as in the case of the Sun, we have the effect of absorption, the continuous spectrum being crossed by dark lines in the positions in which the surrounding gas, if alone, would show bright lines. A gaseous mass under pressure presents an irregular spectrum, partly bright and partly shaded. It is evident, therefore, that the spectroscope cannot absolutely determine whether a body is solid or gaseous, and it is quite probable that stars similar to the Sun are entirely gaseous, while the abnormal appearances caused by pressure give rise to considerable uncertainty in the interpretation of certain spectra, some lines being widened symmetrically, some unsymmetrically by being intensified at one side only, giving an appearance of shifting, some fringed and some suppressed altogether. Banded spectra are attributed to the presence of compounds. The first classification of stellar spectra was due to Angelo Secchi in 1863, and was based principally on the prominence of blue, yellow, or red in the spectrum. His first and most numerous type contains white or bluish-white stars, like Sirius and Vega, showing a colored spectrum with broad bands of hydrogen and fine metallic lines in the brighter stars. Type 2 consists of yellowish stars, as Capello and Arcturus, whose spectra resemble that of the Sun. Type 3 principally of red stars, as Antares, showing hazy bands and dark lines. Later, Secchi distinguished a fourth type, deep red stars, with a spectrum consisting principally of a collection of lines in the yellow and red, resembling a band, with another faint band in the blue and a bright one in the green. These are called carbon stars. Wolf-Rayet stars, named from their co-discoverers at the Paris Observatory, were later still ascribed to a fifth type. Their spectra are composite, as if a continuous spectrum had superposed on it an absorption and an emission spectrum, denoting glowing gas under peculiar pressure conditions. This is one of the types almost confined to the Milky Way. H.C. Vogel of Potsdam, formerly of Bothkamp, introduced subdivisions of these classes, merging the Wolf-Rayet stars into the second class. Thus, 1a is as described above for the first type. 1b is similar, but the hydrogen lines are missing. 1c shows both hydrogen and helium lines. This class also is more frequent in the Milky Way. Similarly, class 2 is in two divisions, the second containing the Wolf-Rayet stars. Class 3 is also divided, according as the bands are more prominent at the red or violet end. It will easily be inferred what is meant by Sirian, solar, Antarian, and helium stars. A far more complete classification has been adopted for use in the Draper Memorial Catalogue, Miss Maury having recognized that the boundary between one class and another was often no more prominent than variations among stars ascribed to one class. This Harvard subdivision is more minute, therefore, and the number of groups is 22, each subdivided into classes. 5 of the groups belong to a helium type called Orion stars, as most of the bright stars in that constellation belong to it. They are rich in hydrogen lines, but show also nearly 100 others, mostly not identified with any known elements. In addition to all these gradations are many stars assigned to a convenient temporary class, called stars with peculiar spectra. The recognition of characteristic spectra in the work of the Draper Catalogue is responsible for the large number of variables, and comparatively also of new stars, announced from time to time by Professor Pickering and Mrs. Fleming. But having reached this classification, the next step is to interpret it, and here, as is often the case in partly speculative work, authorities differ. One order of development, assuming an original nebular condition, makes Orion or helium stars the first stage, as they appear to be of low density and frequently have nebulous appendages. All seem enveloped in helium, but they are graded by Miss Maury, according as they show more and more decided traces of rather denser materials, as silicon, calcium, and magnesium. A few also disclose oxygen absorption, but in general practically no atmosphere is present, as there is outside the Sun's photosphere. Very little atmosphere is shown by the next group, Sirian stars, so their spectra are traversed by fewer lines than that of the Sun, but those of hydrogen are so conspicuous that a star of this class, Vega, was the first to have its spectrum photographed by Huggins in 1879, disclosing a series of lines only completely obtained with difficulty in the laboratory by M.A. Cornu, using a strong spark through a tube of pure hydrogen. This set of lines was the first to be recognized as a series, with wavelengths obeying some sort of law. If, from a given point outside a given straight line, a set of other straight lines be drawn, each making with its neighbor the same small angle, they will intersect the given straight line in points whose consecutive distances increase faster and faster away from the foot of the perpendicular from the given point. Huggins' hydrogen series divides the spectrum in a similar manner, and Balmer's law, published in 1885, is an empirical law approximately representing the numerical facts. Other series have been found for other substances, also obeying Balmer's law, and in particular a second series of hydrogen lines was picked out by Pickering in 1897 in the spectrum of Zeta Puppis, adjudged to belong to the helium group. As this series has not yet been produced artificially, its identification rests on the fact that it is exactly similar to the Huggins series. Just as in the case of a point and a line, a fresh series could be obtained by using a slightly different angle, starting from the same perpendicular. This digression has rather taken us away from the Sirian type, but we may note the stages of evolution through various classes of this group by the relatively diminishing prominence of the hydrogen lines and the increasing show of metallic ones. Sirius itself shows an overwhelming preponderance of hydrogen lines with a few enhanced lines of silicon and magnesium and some others. The term enhanced is applied by Lockyer to lines which show more strongly in spark spectra than in arc spectra obtained from the same substance. The next type, solar stars, show hydrogen lines in a subordinate position compared with metallic lines, the Sun itself showing only 4 hydrogen lines, and Capella, the acknowledged pattern of solar stars, owes its extra hydrogen lines in the violet to the companion star spectroscopically discovered by Campbell and Newall in 1899, which belongs to a group between Sirian and Solar stars, of which Procyon is an example. The calcium absorption is the strong feature of this class, and we have already noted its importance in the case of the Sun, especially in regard to the prominences of the chromosphere. The existence of the atmosphere in these stars causes considerable variation from the exact solar type in some members of the group, such as Arcturus and especially Aldebaran. Aldebaran, however, approximates to the group of red or Antarean stars, with banded spectra remarkable for flutings. A fluting is a set of lines like the Huggins series of hydrogen, but set very close together, giving a shaded appearance. Of the 10 characteristic bands prevalent in this group, and long chemically unknown, Professor Fowler in 1904 identified 8 as belonging to titanium or titanium oxide. These bands signify strong absorption, and it is this token of a dense atmosphere that distinguishes the group, the absorption being due to 9 or 10 metals, of which calcium and iron are the most prominent. About 1 in 7 of this class is a variable. There is no hard and fast line to be drawn between helium and Sirian stars, or between Sirian and solar, so that it is generally surmised that the successive gradations show regular stages of evolution obligatory on all suns. But between solar stars and red stars the gradation is not so regular. There are missing links. Moreover, Professor Hale considers that the carbon stars of the next class do not represent a stage beyond the Antarean, but an alternative line of evolution for solar stars. Hale himself, assisted by Ellerman, succeeded by 1903 in obtaining spectrograms of carbon stars, the difficulty caused by their weakness in photographically active rays being at last surmounted by using specially graded isochromatic plates for 4 successive sections of the spectrum, and by exposures ranging up to 24 hours in duration. A feature of their results consisted of cyanogen flutings in the blue part of the spectrum. They show many lines widened in sunspots, but no enhanced lines. It is urged against Hale's theory of the evolution of carbon stars from solar stars that they are at a much greater distance, and on the whole in a different direction, since, as we have seen, they are very uncommon outside the Milky Way, while the opposite is the case with solar stars. Gaseous stars show bright and dark lines belonging to the same substances, the first of this class, Gamma Cassiopeiae, having been noted by Father Secchi in 1866, and soon followed by Beta Lyrae, each showing a few bright hydrogen lines. A curious feature of these stars is the fact that the red C line of hydrogen, for instance, is sometimes bright and sometimes invisible, which, although recognized in Beta Lyrae, a known variable, as being dependent on the phase of its own light curve, is quite as conspicuous in Gamma Cassiopeiae, which is not regarded as a variable in the ordinary sense. The Wolf-Rayet stars, also gaseous, show no variability, either of light or spectrum. They resemble helium stars to some extent, but their helium lines are not conspicuous, and their affinity to the nebulae is almost as great as to helium stars, so that they are sometimes regarded as an intermediate stage, a fundamental difference, however, being that the persistent bright lines in gaseous stars are one in the blue and one in the yellow, while in the nebulae, as we have seen, these give place to a nebulium line in the green, and in spectroscopy yellow and blue do not produce green. In the valuable Atlas of Representative Stellar Spectra, the fruit of many years of devoted labor by Sir William and Lady Huggins, which appeared in 1899, a scheme of evolution is given from comparatively cool nebulae, growing hotter by degrees through progressive gradual condensation, so long as they remain entirely gaseous, until a maximum is reached, after which continued condensation tends to partial solidification. The gaseous constituents become proportionally less, the law of compensation becomes less and less applicable, and the temperature diminishes. Some theories used to start with an enormous temperature, but most now agree that this is not only unnecessary, but improbable. The chief differences between different temperature classifications are caused by the doubt as to which class really represents the hottest stars, and which groups belong to the cooling stage, and which to the earlier increase of temperature. In Lockyer's meteoritic hypothesis, published in book form in 1890, after appearing from 1887 onwards in a series of communications to the Royal Society, the evolution was traced from nebulae through 7 stages: gaseous, Antarian, imperfect solar, Sirian, true solar, carbon, and extinct. This arrangement, suggested before the distinction of helium stars as a separate group, makes Sirian stars the hottest, whereas Huggins' later series actually commences with Sirius. The plausible assumption from terrestrial analogy that white stars are hotter than yellow and yellow than red cannot be enforced, as the quality of the light received from a star is almost entirely controlled by the outer envelopes, which are at a totally different temperature to the interior mass. Other evidence, such as the low density of helium stars, is far more trustworthy, and is regarded as fixing helium stars as the first stage, not only by Huggins, but also by F. McLean, whose survey of the spectra of the bright stars in the northern hemisphere was supplemented by him with an extension to the South Pole, obtained with the Victoria telescope which he presented to the Cape Observatory in 1897. Lockyer himself has also considerably modified his first order of classification, and now agrees with most other systems in assigning the highest temperature to Orion stars. His latest classification suggests Gamma Argus as a type of the hottest stars, the ascending series starting with Antares, and the descending series ending with Piscean stars, type 19 Piscium, the former series including among other typical steps Aldebaran, Alpha Cygni, and Rigel, while the latter includes Algol, Sirius, Procyon, and Arcturus. Gaps are, however, indicated in both. In the case of unequal double stars, the frequency with which the chief star appears to belong to the solar and the companion to the Sirian type is explained by Miss Clarke on the hypothesis that in giant stars the greater effect of gravitation accelerates the evolution, so that, contrary to expectation, the primary has reached a later stage of development than the secondary. But though there is really no analogy with the solar system to justify this disappointed expectation, the researches of Lewis in the Struve memoir already cited tend to contradict, not the explanation, but the actual facts, by showing that the supposed chief star is in reality the secondary in many cases of the kind. As regards the 2 red groups which, as we have seen, Hale considers to represent alternative tracks of development of solar stars, and which in Lockyer's scheme are of quite opposite tendencies, one rising to one solar type while the other marks the fall from another, there is little analogy to help us, but the fact that in one class the flutings shade towards the red, and in the other towards the violet, would seem to indicate that one is a case of rising and the other of falling temperature, were it not for the difficulty of accounting for the presence of compound substances in the earlier stages of evolution. The more recent researches of Hartmann and Eberhard at Potsdam attribute excessive brightness not to transcendent temperature, but to electrical luminescence. This pronouncement, rejecting the assumption involved in the ordinary view of enhanced lines that the spark is hotter than the arc, is of considerable importance as emphasizing the impracticability of explaining all types on a temperature basis only. Dr. W. E. Wilson of Daramona, Ireland, is another strong opponent of the temperature classification, and recent researches of A. W. Claydon on the subject of cloud spheres and photospheres tend to show that similar effects can be produced by diminishing the mass instead of increasing the temperature, so that a large hot body might show precisely the same spectrum as a much cooler and less massive one. Such reasoning would go far to explain the inverted relation of brightness and mass of binary stars referred to by Lewis in the Struve memoir. The great interest and importance of research of this kind will be readily conceived from the most inadequate sketch, and it is not surprising that some of the world's greatest telescopes should be employed upon it. The first spectroscopic star catalogue was published by Vogel at Potsdam in 1883, containing over 4,000 stars from one volume of Argelander's Zones, from 2 degrees south of the equator to 20 degrees north of it. In the preparation of the Draper Catalogue, 1890, the instrument used discarded the slit as unnecessary for stars, and substituted for the cylindrical lens then used to give width to the spectrum an arrangement by which the star slowly crossed the field of view in a direction parallel to the edge of the prism by which its light was analyzed. In 1899, the great Potsdam 31.5-inch refractor was mounted, and spectrographs arranged for use with it. The Bruce spectrograph in conjunction with the 40-inch refractor of the Yerkes Observatory, in the hands first of Hale and then of E. B. Frost and W. S. Adams, was at work about the same time. Campbell's observations with the Mills spectrograph on the 36-inch Lick refractor commenced earlier in 1895, and the southern extension under W. H. Wright with the new Mills spectrograph dispatched for 2 or 3 years to Santiago, Chile, was installed in 1904. Other recent installations include a spectrograph employed by V. M. Slipher in connection with the 24-inch Lowell telescope, and an elaborate thermostat to secure uniformity of temperature in the spectroscope attached to the 24-inch Victoria telescope at the Cape. With so many ardent workers in the field, it is not surprising that progress in this comparatively new branch has been rapid. We have noted, for example, that the discoveries of spectroscopic binaries, commenced in 1889, reached 146 in 1905, and of these, more than half were discovered with the Mills spectrographs at Lick or Santiago, 75 to be exact, the Yerkes Observatory, which started later, claiming 44. Moreover, progress is steadily being made in the direction of obtaining spectra of fainter stars, and side by side with this goes on the examination in detail of the spectrum of portions of the only star available for this purpose, the Sun, and with them both the necessary complement of the other branches, the spectroscopy of terrestrial substances in the laboratory. And with it all, vast problems yet remain. The more we learn, the more there is behind, and the more fully is recognized the necessity for cooperation to lessen the waste of time involved in needless overlapping, to guard against the omission of sections, to ensure that economy with efficiency shall not be a mere parrot cry. The principles of the Astrographic Conference and of the International Solar Union have already extended into stellar spectroscopy, which has not yet seen its jubilee. End of chapter 32.
Chapter 33 of A History of Astronomy. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Daniel Wolfe. A History of Astronomy by Walter W. Bryant. Chapter 33, Conclusion. Where then do we stand? Small creatures on a small planet revolving about a not very big sun. Jonathan Swift's often misquoted lines, "So naturalists observe, a flea hath smaller fleas that on him prey, and these have smaller still to bite him, and so proceed ad infinitum," embody a rule that works equally well or badly both ways. In the case of the fleas, the upper limit is fairly obvious, but with the Earth it is the lower limit that is familiar. Lambert, a contemporary of Laplace, speculated in the opposite direction, arguing by analogy from satellites to planets and from planets to the sun that our sun with other suns might be circling around some vaster orb, which, with its compeers, might form the family of a still mightier one, so on, if not ad infinitum, yet far beyond our powers of proof. No central suns were or are apparent, so Lambert conjectured them as possibly non-luminous. Dark bodies do exist, as we have seen, and may be far more numerous than is usually supposed. They might frequently occult some distant star without our ever noticing it. Their existence is sometimes suggested to account for the apparent thinning of the stars in distant space by those who doubt the finiteness of our own universe. But limiting our ideas to what we can see, there is room for much diversity of speculation. Within this restricted region, there certainly appear to be some vast stellar systems far exceeding the dimensions of a simple binary. Mizar, as we have seen, is a spectroscopic binary and also a visual binary. Alcor the Rider moves with it, and so apparently do all but the outermost two of the 7 stars of the Plough. Other systems are equally distinct, the famous Pleiades, for instance, and judging from their similarity of spectra, most of the bright stars in Orion. It does not now seem possible to regard small nebulae as island universes, in Herschel's phrase, distant galaxies as vast as the Milky Way. They seem rather, since Keeler's estimate, to represent the dispersed material of which the stars are made, and to which dead suns may yet return as dust to dust, possibly disrupted by collision with other dead suns after a short period of bright existence as temporary stars. Such a theory of Nova Persei and its nebulosity is not quite impossible, though strongly discredited on account of the velocities involved. It may be urged against the theory of celestial evolution that each stage of growth should be equally represented, but this could not be expected unless the stages are of equal duration, which is in the last degree unlikely, even during visibility. New stars are uncommon, and few, even dull red stars, are known to have disappeared, but this may only show the quickness of these stages compared with the millions of years demanded for the life of a star, which is by every model of reasoning probably but a small part of its actual existence, for most of which it should be invisible. And in this invisibility may lie another view of the finite universe. We know from Newcomb's careful estimate that suns, except in recognized binary and multiple systems, do not cluster closely. He computes that only one is to be found on an average in every 8 units of space, his unit being a sphere whose radius corresponds to a parallax of a second of arc, or more than 3 light-years. Thus, a sphere of a diameter of some 13 light-years will contain on an average one visible star. But it has often been pointed out that any regular distribution of stars, however scanty, in infinite space, must lead inevitably to the conclusion that some star must lie in every direction. It has been suggested that from the distant spaces light has not yet arrived, though on its way, but this is rather making an assumption as to the time of starting, for which no data are given. It seems, however, quite as effective to treat the matter quantitatively on the hypothesis of a short life period. Suppose, then, the visibility of a star to last for 1% of its existence, between one shining and the next, if we carry the evolution to its logical continuation. It follows that if stars lie in every direction in space, there is only one chance in 100 that of a possibly infinite number of stars in a straight line, the nearest one should be shining. In other words, there is only one chance in 100 that a star will be seen in any particular direction. The 100 is only given for convenience of illustration. 1,000,000 would be equally probable or improbable, as we have no data by which to test it. This illustration is not given as a serious effort to combat the idea of a finite universe. It is a practical impossibility for the mind to grasp the conception of a universe finite or infinite. The intention is rather to show the inherent weakness of many abstract speculations. Some generalizations are definite and unmistakable. The visible universe is almost symmetrically divided by the Milky Way, where helium and gaseous stars and nebulae do congregate, while other nebulae are rare, so that it may easily be regarded as the fundamental plane of the universe. We may be, as some maintain, practically in the center of the space bounded by the galaxy. Even if so, it seems the wildest speculation to suggest, with Dr. Wallace, that the solar system is the only system, and the Earth the only planet, in that or any other system, fitted for the abode of man. Shifted 1,000,000,000 miles in any direction, we should still be in the center, but it is not so certain that we are. Newcomb proposes a reference to the astrographic survey, when completed, to decide this question. Easton, following out Keeler's pregnant suggestion, sees in its rifts and other irregularities evidence of spiral structure in the galaxy itself, with the solar system eccentrically placed between two successive wisps. It is also inferred from the fact that stars of Secchi's first type are twice as frequent in the galactic zone as in the rest of the sky, while his second and third types are evenly distributed, that we are dealing with separate systems. Hence, Pickering and others treat them separately in regard to such problems as the determination of the solar apex, as we have had occasion to remark in previous chapters. It may also be that the whole cosmic cluster is not in the shape of a grindstone or lens, with its greatest extension round the plane of the galaxy. Its approximation to the ordinary spheroidal form was suggested by Radu 20 years ago. We cannot see stars further off in the galaxy than elsewhere, at least so far as we know. Stars without sensible parallax and stars on the limit of photographic visibility are found in all directions, and as a set-off against the preponderance of stars in the galaxy is that of nebulae outside it, seeming to cluster round the points furthest from the plane. If this be so, we may regard the Milky Way as the equatorial zone of a rotating universe, and explain the thronging of brighter stars there on the analogy of the bulging equator of a rotating planet, or by the possible acceleration due to increased velocity of the evolution of clusters from nebulae, or by the actual brightening of stars from the same cause, which also may modify or codify the distribution of certain types, yet leaving many subordinate systems within the confines of this universal globe to continue their almost independent motions. This is but speculation. None may read the riddle clearly. We can but peep about, not necessarily to find ourselves dishonorable graves, nor merely to magnify the scientific achievements of our fellow men, but rather to marvel at the mighty works of a supreme intelligence, and to convince ourselves of our colossal insignificance. End of Chapter 33. End of A History of Astronomy by Walter W. Bryant.